So my name is Stefan Erisson. I've been in Boulder for 20 odd years, 22 years. I'm from Sweden, so you hear a little bit of accent and looking for words, that's that. So I started as a postdoc here, working with Bob Ergen's group, and in those days, I was working on the FAST satellite mission. That was an auroral high latitude polar orbiting mission in the ionosphere, looking at E cross B drifts and aurora and such things. And from that realm, I then moved myself a little bit higher up because there are field-line currents and such things, and they connect upward to the magnetospheres. And so I got interested in the magnetospheres. But today, I'm going to talk about the topic of reconnection. I'm going to talk about multi-spacecraft missions and why do we need them and what cool things can we do with that. Now, this is a nice picture. This was the particle solar. Oh, this is a little bit ahead of me. There. I wanted to show this. This is just it's a nice photo taking of a partial solar eclipse from the coast of Australia in April of this year. And what you can see is, of course, the moon blocking the sun, so we can see what? Anyone? What is that sticking out from the sides? What do we call that? Streamers, yeah, it starts with a C, crown. Corona, right? It's the corona. You're looking at the corona, the outer layers of the sun. There are things sticking out of that, and there are current sheets and things. So that's where we're heading. We're heading to the current sheets. Let's talk about scales a little bit. Let's put things into perspective, right? So that's a blue arrow in the middle. Let's call that 1 solar radii. So how long is that little streamer pointing out? Well, it's about 9 RS where that arrow is pointing, 9 solar radii. And 1 Earth radius is 6378 kilometers, which means that that's 109 Earth radii, 50 planets of our planets, right? So the particle solar probe is going to approach close to this distance very soon as the closest perihelia to taste the corona at this close distance. That's in December 24, 2024. It will then travel at about 1 RS per hour. That's fast. That is actually about 230 times the speed of a bullet out of a gun. All right, it's fast. Let's look a little bit closer at the sun, at the corona. Now we start seeing the structure. Remember, this is it's a photographer, so he's trained in astronomy, but it's amazing what you can do these days with technology that we have. So what are we looking here? We're looking at structures within the corona. And we can call that little thing pointing out there a helmet streamer. Now, there are helmet streamer and pseudo streamers. A helmet streamer is really just like a loop, right? Where the field is coming out from one direction and then coming back down the other side. So it's just one loop of a magnetic field. That we call a helmet streamer. That might not be a helmet streamer because we're looking at projections. We're looking at things, that could be 3D structures here. But it could be that we're looking at a magnetic field in opposite directions on either side of that little structure up there. Well, today I'm going to talk about those current sheets. We're going to talk about quite a few things. We're going to talk about magnetic field rotations from the really wide heliospheric current sheet, how wide that is, and we're comparing that to the narrow, quote unquote, magnetospheres current sheet. Then I'll go through the missions out there, a brief introduction to what a tetrahedron is, and how we can use that formation flying of spacecraft into getting parameters that we need, just for example, like current sheet, current density. And I'm going through, talk about the reconnection process of current sheet, schematic overviews, to be or not to be frozen in. And that's the generalized Ohm's law. And I'm going to derive that a little bit on the fly here for you. And you have that as maybe as an activity this afternoon too, because I think that is sort of a central equation, if you will, when you're looking at magnetic reconnection. So we'll get to that. And then finally, observations of these reconnection jets. So remember that picture of the sun up here, and there are these helmet streamers pointing out. And so that's what this is here, a schematic. This is now looking at the plane, equatorial, ecliptic plane, where these lines are the magnetic fields pointing away from the sun as a positive polarity there, and then negative polarity magnetic field pointing toward the sun. Where those two fields meet, we have a rotation of the magnetic field, and that's then by Ampere's law, a current sheet. Then some people here in 2019 kind of modeled that heliospheric current sheet. Remember, let's go back here for a sec. These are the magnetic field lines, right? And they're warped up or a bit by the Archimedean spiral as the sun rotates. But that's the magnetic field. The current sheet is sort of a slice through that at some angle in this region here. So imagine you have a sheet, big sheet, and it becomes warped. And why does it become warped? Here are two different examples. It depends on that dipole angle versus a rotation axis. So the rotation axis and the dipole axis, the more of an angle you have between the two, the more of this warpiness you will get of the whole big heliospheric current sheet structure. How big is it? How thick is it? Because when we eventually get to reconnection, then we want to know, reconnection only happens when you have a thin current sheet. But this is a really wide current sheet. It's one of the biggest that we know of in our heliosphere, in our solar system. So there are two references here. One was referring to a minimum thickness of the current sheet of 3,500 kilometers with a median of maybe 9,000 kilometers. Whereas another paper here looked at 212 events and they found an average of 64,000 kilometers. So that's about 10 RE. That's a really thick layer. Hard to reconnect, hard to imagine it reconnecting when it's that thick. Reconnection is something really, needs something really thin. So how does that compare to the Earth's magnetopause? So this is then a picture from the side of our magnetosphere, and the cursor is moving a little bit slow here. So imagine the solar wind coming toward our planet with the magnetic field pointing southward. That southward magnetic field is opposite to the Earth's magnetic field here at the day side. So we can get this reconnection site here, but there's also reconnection here in the tail. Where's that current pointing at the magnetopause? Well, this is a 3D kind of schematic of that. And these are then the currents forming here at the day side magnetopause. And it's because ions will come from the solar wind and then will start gyrating one way. The electrons will start gyrating the other way because of the V cross B force on them. But that happens all along that surface. You get that net current going down from dawn to dusk. Now let's talk about multi-spacecraft missions and the tetrahedron. Famous 11-year sunspot cycle from 1900 to 2000 year plus. Numbers on the top marking the name of that solar cycle, 14, cycle 19, 22, and so on. We're in cycle 25. There are three lines here at the end, vertical lines, the green, the blue, and the red. Okay? Those are launch dates of 3 multi-spacecraft missions. The first one to be launched in a multi-spacecraft fashion was the cluster satellite mission. 4 satellites for the first time flying in a formation ion scale. Then we have the Themis satellite mission consisting of 5 spacecraft, but they didn't have that requirement to be in a tetrahedron because they were looking at things in a minute tail. MMS then is the first 4 spacecraft mission, but at a much smaller scale. They're much closer together. Then, young people here, look out for, in 5 years from now, in 2028, we have the Helioswarm mission consisting of 9 spacecraft to be launched and to study turbulence, reconnection, and all that sort of exciting stuff. This is what they look like compared to a human being, how big they are, the 4 cluster satellites. They have lots of different instruments on them, and they were launched in 2001. So what is a tetrahedron? This is a regular tetrahedron, regular meaning that it's a perfect tetrahedron, where in each vertex of this geometric structure, there's a satellite, right? So now when you have something flying in that formation, you can start trying to get some handle on the current density. Now, this particular formation, you can't just fly that all the time around the Earth because the Earth's gravity is pulling on all the satellites, and that will take a lot of fuel to make sure that they stay in that formation throughout the orbit. So we only then focus on the region of interest in the gray area, where we're really interested in the science objectives of the mission. So they would have an active control region where we then move the spacecraft to use a little bit of fuel just to correct them a little bit, to try and maintain as close as possible to a tetrahedron. It's not perfect anytime. Well, you'd like it to be, but it just takes a lot of fuel to do that. So why fly it? Well, we need to know the current density in space due to its importance, such as magnetic reconnection. The MMS particle instruments, the FPI instruments that measures the moments of the ion and the electron distribution functions, they do that at such a high cadence and at such good quality that we can actually get a local current density measure just from taking the density that we measure times the charge E times the difference of ion and electron velocity vectors. Then we get the vector of the current. But before MMS, those high quality measurements were not available. So you had to get that in some other way. Even with cluster, they didn't have good enough measurements to do that, right? So we use something called a curlometer technique. With that, well, with flying in a tetrahedron, it's not just like curlometer, which is a rotation of the magnetic field that you get. You can get gradients of anything. You can get the divergence, you know, the nabla symbol, right? Time for the magnetic field. Then you get div B. You can get divergence of other things too, if you have a good enough formation. So this is how you do it. This is taken from a paper by Malcolm Dunlop. He was one of the first, I think, putting this into text. It was 1988. So if you have these 4 spacecraft flying at those points, you can get your curl of B by doing some algebra here, and I'm not going to go through all this text here, but you get the curl B arising from Stokes' theorem to get this equation here at the top. So now you have these differences between the spacecraft, and you have the differences of the measured magnetic field, and you cycle through all of those, and then you can get 3 equations for 3 independent components of the curl of B. You basically take it's a cross product of the difference between 2 spacecraft to the other, and you get those currents 2 through 4, 1 through 4, etc. So the near Earth space, let's just have a little bit of reminder of boundaries in space, and maybe have you talked about the magnetopause yet? Magnetosphere this week? Anybody? You know all this, right? If you don't, just raise a hand, okay? Flag me if I talk over or below it. But what you have here is a view of our magnetosphere, right? You got the sun on your right, the X direction. You got the green arrow, that's the dawn-dusk direction, and we're looking from above. We're looking at 2 surfaces. The outermost we call the bow shock. Then we have this greenish region we refer to as the magnetosheath. Then you have this white mesh inner boundary. That's a magnetopause. It's the outer edge of our planet's magnetic field. Inside of that, it's influenced by the Earth's magnetic field. Outside, it's the sun's magnetic field dictating what's going on. We have pauses everywhere, right? We have the heliopause. outermost boundary of our whole, sun's influence regime, the heliosphere. We have 2 spacecraft missions flying here, going around and around in their orbits. The one here on the day side, that's a cluster 3 mission, flying information. You only see 1 dot because the 4 spacecraft are too close to be seen here together. It would just look like too messy. Then we have the geotail. And they're crossing all these boundaries. But what does it look like if we look at the data? Right. This is what it looks like. This is a plot you see on the bottom from 0-100 to maybe it's a full day even. So I have numbered some stuff here in the letters on the top, A, B, and C. And I have marked some two boundaries, the 1 and 2. And there are a lot of data from top to bottom. On the top, it's the total magnetic field strength. You can see that goes from high in A, somewhat high in B, and very low in C. So that A region, that's inside our magnetosphere. So if you look at some other components here we have the components of magnetic field, the density. We see that's a low density region with a high temperature, and this is a log scale with a high field. So this is a magnetosphere. Then we cross into this region I call the magnetosheath. In between, there's the magnetopause. The magnetopause is not just a very thin region. It's a boundary layer. It has a finite thickness. It's infinitely thin. So there are 2 lines here. And then we have, what else do I show? I show the velocity X, Y, and Z components of it in the GSE system. I have the Alvean Mach number. So you can see here that in the solar wind, we are super Alveanic. The flow is moving faster than the local Alvean speed. Then we come into the magnetosheath where it's subalveanic. Here we see the dotted line is 1. And yeah, that's it. Yeah, you may want to ask yourself, what's going on here? Why is the ion density not the same as the electron density? It should be the same. It should be quasi-neutral. Well, the instrument was in the wrong mode. Yeah, question? Oh, start and stop. Okay, good question. It's essentially the start of the rotation of the B. So you can see the green line here. I hope you can see that. It's going from a slightly positive to slightly, to the negative value here. So it's a finite thickness of the rotation of the field. The magnetopause consists of a current. It's a rotation of the field. Good question. Another one. Yeah. So we get the Alvean speed. That's the B over the square root of mass density time rho times mu naught, right? That's Alvean speed. So you can get that from the local measurements of the magnetic field and the density, assuming protons. Now, in the solar wind, the Alvean speed that you get is lower than the actual motion of the plasma itself, V. So V divided by VA is a high number. Okay. Now, what I pointed to here is at that boundary, we have reconnection jets. Okay. Why do I think that? I've been looking at them for a long time. But you can see that in the beyond that, in the magnetosheath in the solar wind, it's going at what VY like less than 100 kilometers per second. In that region, it's going up to upwards of 300 kilometers per second. There's a large jump in the velocity in that direction. It's a jet. So let's talk about the reconnection process here. Current sheets. This is sort of the one bulk of this. Has been an introduction so far. This will be inviting you to this whole concept in the world of reconnection at current sheets. How does it look like? What are X lines? What are X points? What are diffusion regions? Now, X points and X lines, that's because it looks like that when you look at it, right? But remember, there are many, many different scales. We all live in a multi-scale universe, okay, where you have the big heliospheric current sheet, and you have really thinner current sheets, and all the scales in between. Okay? So when you point an X, that's because the region is so darn small that most people we put an X there. But let's try and forget the X. It's a region. It's a finite region, but we can get there. All right, let's get to it. So this is taken from your textbook. And, well, not the picture. The picture is from Jim Birch and Jim Drake here in 2009. So imagine you have this layer between two different plasmas, the green plasma and the orange plasma. Each of them has a field pointing in opposite directions in this plane. Doesn't have to be just in this plane. We say this is anti-parallel directed fields, but the total field in space could have a component pointing at you or toward the plane here. But let's make it a little bit more simple here. And begin, we just look at these components of the in-plane. For some reason, these two plasmas, the orange and the green, are pushed together. They're driven together. There are different motions of the plasma all the time. So let's assume that they're moving together at a velocity v from either side. And in that region in between, it's a current density layer. It's a current layer. Why? Because of the rotation of the magnetic field. That's why we need that J from tetrahedron. So nothing has happened yet. There's a plasma element red and there's a plasma element blue. Well, what do you mean by that? Well, particles are really just gyrating. They're moving around the magnetic field. They're stuck to the field. They can move along the field by whatever velocity, but they're gyrating about the magnetic field. Ions have a big Larmor gyro radius. Electrons have a tiny little tight circle around because their mass is so much smaller. So at some point in that blue, we have, those ions and those electrons moving around, gyrating. They're all happily, and they're connected. They're connected by that magnetic field line. Will they always be connected? No. Sometimes it fails. This whole feline concept and their term reconnection can be used to refer to a changing connectivity or the decoupling of their motions relative to the background magnetic field. Reconnection occurs whenever this approximation of frozen in flux fails. Frozen in, well, have you heard of, the E cross B drift? They're moving at the E cross B drift. Oops. Now, let's call this at some initial time. At some time here, B, the fields reconnect. They merge. They're being pushed together, really thin layer, locally thin layer of the current sheet. Remember, the current sheet can be thicker outside, but it's locally thinner here. So it reconnects at the X, but if you zoom into it, it's really a region. Now, at a somewhat later time, C, those two elements are not connected. They're separated. The red is moving up because that field has a tension to it. It just jets out. So they're going from being connected to disconnected. Reconnection happened in that magic region. Here's another way of looking at it. Fields are being pushed in, they're moving in from both sides to that small region of space. Then those two fields, the red and blue, have been connected and they move away from that. So there's an inflow from top and bottom, and there's an outflow on the sides. Now, particle drifting with the field from the top, they will now find themselves in that jet region of that magnetic field moving away from it. So when the magnetic field moves, the particles move with it at this E cross B drift. So if there's an E cross B drift, the yellow arrows, there must be an electric field, E minus V cross B. That's the frozen in. So when we say that if the electric field, you can measure the electric field, you can measure the velocity of the magnetic field. If they are, E plus V cross B is 0, it's frozen in. Particles are moving with the field. There's nothing exciting reconnection-wise happening. 2D versus 3D, right? So this is if you imagine this plane, 2D plane on your this slide, let's try and move that away. Then it's not really an X point, becomes sort of an X line. X line here, this region. So if you think of that, moving that picture, huh? Yeah. One more. The other way? This way? This. Yeah, good question. So the displacement current, this is the full Ampere's law. So this is so the rotational B is mu naught times J plus a displacement current. Okay, but in a steady state situation, and if it is steady state for just a short period of time, but that time is then longer than dE dt, then we can assume that it's small. This is another beautiful picture of the whole process. Let's look at leftward field lines on the top, pointing in the other one on the bottom. For some reason, the plasma is being pushed and it's driven inward by this electric field minus V cross B, and then it jets out. So in this region, there's a topology change of the field, and the particles are disconnected from one another, decoupled, and there's heated plasma. So this region is really a reconnection diffusion region. That's the little box that you see here. That's where the charged particles, the ions and the electrons, are no longer frozen in to magnetic field. So E is not equal to minus V cross B anymore, and the full particle motion is not a simple gyration about magnetic field. We call that the reconnection diffusion region. Yes? It's okay. Yeah, the source of the electric field is a motion of the field lines, and the particles are frozen into it. So the motion of field lines, you can think of, for example, the magnetopause. The motion of field lines there is that the solar wind is pushing those fields against the Earth's magnetic field. So in that sense, you can have that motion of field is coming at. Okay, we call that a driven reconnection situation. An undriven or more spontaneous reconnection is there are motions all the time in the plasma. Yeah, yep. Again, it's a scale within a scale. So yeah. The reconnection jet regions to the left and to the right here, that's when the newly reconnected fields are strongly bent. So it's a tension of the magnetic field, and that pushes in the J cross B sense to push the plasma out of it. So it's strongly bent field has a J to it, and that J cross the magnetic field locally, which is pointing up and down, is pushing that plasma away. Here's another beautiful picture from a simulation, a blue and a red region. Those are the two jets in the Vx component going away from the X line in between the two. We have a normal to the current sheet, and we can simulate the time evolution of plasma in kind of two big different ways. One is an MHD kind of model, fluid methods. And so they capture the macroscopic system evolution. And small inaccuracies can develop at small scales where the MHD breaks down. Okay, so reconnection region is one such region. Then we have to go to something else. We call it kinetic methods or particle in cell PIC codes. And they aim to describe the full motion of the electrons and the ions under the influence of magnetic fields and electric fields. So we need the full, all Maxwell's equations and the blast of transport. But they're expensive, so we can't do it everywhere because it's really hard to get to the full mass ratio of 1836. That's the mass ratio between protons and electrons. Also doing it at a 3D is prohibitively expensive sometimes, computationally wise. So you just do it in a small region. Now, PIC simulations suggest that reconnection occurs when a current sheet thins down on the order of the scale that we call DI. Okay, ion scale. So 1 DI, that's defined as then the speed of light over the plasma frequency. So the plasma frequency is squared, is a density, it just depends on the density. Everything else there are constants. So it's a density dependent measure. If you're in a high density region, that plasma frequency will be high and your scale will be low. If you're in a really low density region, a very tenuous plasma, then plasma frequency is also low and the scale will be high, right? But the beauty of this is that the reconnection process only cares some about this DI. So in kilometer sense, you're going for many different, distances and widths. I'll skip that. Then the DI scale is known as, some people call it the ion skin depth or the ion inertial length. And what is it typically? In the solar wind, if you take A's measurements, the A satellite is sitting up at the upstream point, upstream of the Earth, 200 plus RE. So if you take all the measurements from 1991, January 1st, through the end of 2015, you get all your measurements together, and you plot a histogram of all those measurements, you get a median density of 4 per cc. You also get a medium, 100 kilometer, really nice. But that's a bin size of 5 though, so it's 99 or 98 something. Okay, to be or not to be. So here we go, the generalized Ohm's law versus the whole term. So since the E is minus V cross B, just outside that narrow current layer, there has to be an electric field of that same magnitude also inside, just on the other side of that, where the electric field is not minus V cross B anymore. So if it's not that, what is it? So in order to get to that, we must explore the particle motions and the forces that act on them in the small current layer of the current. This 2 through 3 slides on this GOL, generalized Ohm's law. Now, it's important where it comes from and how we get to these electric fields. Why do we need to measure them? Right? So we start with the 2 equations of motion. These are for the particles. 1 is for electrons. The equation 2 here is for the ions. It's the Newton's second law. So we have the force on an acceleration on the left, and with the forces acting on those particles on the right. We have the the force, the E, and then we have the magnetic force acting on them. We can have a gradient in the plasma pressure, and that's also a force acting on the particles, or of course the gravity. Here, the electron, and these are scalar pressures in an assumed isotropic plasma temperature, but we can have, very often you have not that situation. Parallel temperature could be very much different from along the field, could be very much different from the perpendicular temperature. So then this gradient P turns into more of a pressure tensor, and instead of a gradient P, it's a divergence of the pressure tensor. Now, in the plasma, we look at all of them particles combined in the density. So if we put that, then it becomes add the density times, everything there. And by adding these 2 equations of motion for electrons top and ions bottom, we get the plasma equation of motion. Rho times dV dt equals J cross B minus the grad force. Okay, so you've seen that. If we now take equation 2 for the ions times electron mass over ion mass times density, times n there, minus the other equation, and assuming that ions are roughly going at the background velocity, and the electrons that we get from subtraction of the current density, excuse me, and we take that algebra, we get to the generalized Ohm's law. So that's how we get it. We get it from the 2 equations of motion in a plasma with a mass ratio rho. So E plus V cross B is not 0. In the frozen in, everything on the right-hand side is 0. So that's the beauty of this equation, is that it's telling you the sources of the electric field in that region, not frozen in anymore. Frozen in, not being frozen in means that the electrons and the ions are just moving more freely from that field. They're not bound by it anymore. Okay, we have then 3 terms basically here. We have the Hall term in red, that's a J cross B. We have an electron pressure divergence term, and we have electron inertia terms. So in kinetic treatments, the presence of these non-ideal electric fields is what contributes to the violation of the frozen in condition. The objective of the MMS mission is to explore all these right-hand terms, to measure the J cross B, to measure the divergence pressure of the pressure tensor. And in order to do that, you need really high cadence measurements. You get, for the MMS, you have 30 millisecond cadence for the electrons and 150 millisecond cadence for the ions in burst mode. Oops. Okay, so in symmetric reconnection, here's a symmetric PIC simulation. And there's some the grayscale here with the differences white and black, and it's the magnetic field on the top. So the coordinate system here is that X is along the current sheet, Y is pointing into the plane, and Z is normal to the current sheet. Current sheet is in the middle and at 0, Z equals Z at 0 there. So if you take a cut through this PIC simulation in this very middle region, going through the reconnection X line here, if you will, going from bottom to top, this is what they measured in the PIC simulation. First, a little note on the scales. Okay, the mass ratio is 1836, which means that how small is that region compared to the DI scale of the current sheet? Well, DE is 43 times smaller than the ion scale, just by the mass ratio. For example, in the solar wind, we had 100 kilometer dimension for the ion scale. So divided by 43, you get 2.3. So that's a big difference. Okay, we have 3 regions here. First, number 1, that's far upstream. And if you look at the simulation cuts here, we're far upstream where this gray line, what is that? Well, that's VI cross B equals this red line, which is that due to the motion of the plasma there. So E equals minus VI cross B, so it's frozen in. No other terms are important in this region. Everything else is pretty much 0 here. So ions and electrons are frozen in to B. That's the inflow region. In the 2, when we get closer to the current sheet, we start to get a deviation. We see that the VI is not carrying the electric field anymore. Something else is doing it. And that's the purple line. And that's the J cross B term. So in this region 2, we call it the ion diffusion region. The ions are now decoupled. The electrons are not. Electrons are still tightly bound by the magnetic field. It's not until you get to region 3, in the very center here, small scales, that also the electrons are no longer frozen in. And so in this region, what is that term? Well, that's this green line over here that carries the full red line, and that's the divergence of the pressure tensor. Now we're in the electron diffusion region. Let's talk about those things here on the top. Since electrons decouple from the magnetic field closer to the layer than the ions, we get this polarization electric field. So it's pointing toward the layer. We call it Hall electric field. So we have then, it's sort of somewhat white here, and that's pointing upward, and it's black over here, pointing downward. That's a Hall electric field. Here on top, we get a quadrupole. We have black here, white, black, and white. Those are due to the electron motions not being frozen in anymore. We call it the Hall magnetic field. All right? These are 2 signatures of the J cross B term. So now we know that we're in an ion diffusion region when you see that. If you cross through a jet observationally and you see those terms, yeah, you can say that, okay, I see the Hall magnetic field, check. So these streamlines, the yellow, that's the Poynting flux, E cross B. Well, it's E cross H really, but E cross B by mu naught. That's the Poynting flux, directional and energy flux. You can see that it's coming in and it's streaming away from the X line. So there's a directional energy flux moving away from that region, and it's due to these 2 Hall terms in the electric field and the magnetic field. Now, the Day-side magnetopause is not symmetric. It's asymmetric. What do I mean by that? Well, there's a lot of differences on the 2 sides of the boundary. The density is high in the magnetic sheath, and it's really low in the magnetosphere. Magnetic field is really high in a magnetosphere, and it's a little bit lower in the magnetic sheath. So these differences, asymmetries, relative to the boundary. So you need to really simulate it in the PIC code doing that. So here we see that the field lines are tightly close together. This is the high B field side. Here the field lines are apart from one another, separate from one another. It's a low field region. So we can think of the top region here as a magnetic sheath, and we can think of this on the bottom as a magnetosphere. So in that sense, the the Hall electric field is not symmetric anymore. It becomes very asymmetric, and it sits here just inside of the region. And the Hall magnetic fields are no longer 4 poles. They're just 2 poles. So the 2 poles sitting below the blue and the red on either side, they disappeared. Density is actually too low there. Okay, so here's a summary of all of this. The gray box, the ion diffusion region, the yellow box, the electron diffusion region, and these dashed red lines, those are the electrons still frozen in, moving with the field toward the X line, much closer to it. Those motions, those loops of current, electron motion is a current, right? So you get that's where you get these disturbances, perturbations of magnetic field, the Hall fields. I think we will skip the reconnection rate for some other time. This was a set of important papers up until early 2000. People were arguing what is the reconnection rate and what's important. How do you get fast reconnection? The section I just skipped is that if you do Sweet-Parker and you look at this geometry of the region, Sweet and Parker in the 1960s, they came to a reconnection rate that was just way too low. It's not explaining why flares pop up so suddenly and quickly. So in comes these sets of papers. An introduction by Joachim Bern et al. Summarizes the results of these papers. And it shows here that if you just have MHD without the J cross B Hall term from the generalized Ohm's law, it just doesn't do it. It's too slow. The rate of flux is not happening in time. Okay, but if you add that already in Hall MHD, Hall meaning you added that J cross B term, now you see that yes, the rate of flux goes up. So it's an important measure to add that J cross B term. Full particle is that solid line. Let's get to the observations here in the last few seconds here, minutes. So cluster, I'll show cluster and solar wind and talk about timing a little bit. How do we find these things in space? So how do we find them? Well, first you got to find a current sheet. You're going to find a rotation of the field. And once you've done that, you look at the plasma moments of the ions and you see, well, do you see a jet peaking up or down across that layer? You know, if you cross through a layer in space like that, you would like to see that jet, we might say. And if it does, is it moving at roughly the Albion speed in the frame measurement? Now, I talk about LMN here and XYZ. We like to use L for the reconnected field, the jet direction. We like to use N for normal, perpendicular to the current sheet, and M pointing out of the plane. In these different years, the clusters for spacecraft, they were separated at the two closest were at 600 kilometers in 2005. In 2008, the 2 closest ones were only 40 kilometers. So they kept moving their spacecraft around through the mission. These are just 4 years, and they kept moving after that. Right? But the maximum distance between any two in that formation was much larger. This is in kilometers. Remember that DI scale that we're interested in, 1 DI is where the current sheet breaks down. Well, divide it by 100, and you get to these numbers. So this is the separation of the spacecraft through the different years. So if you're interested in various things, you know, you can pick your year here. How do you find current sheets? Well, on the right here, you have a set of measurements. It's roughly 3-4 minutes. Yeah, it's 4 minutes long. From the top, you have the total field strength in the solar wind now. It's roughly, 5 nanotesla. Then you have the X component of the magnetic field, a second panel from the top. And yeah, you see rotation. It's not a simple gradual rotation. It's actually bifurcated. It's like 2 sudden motions. Huh? So that's the X. What does the VX component do then? Is there a jet there? So we found our current sheet. Is there a jet? Well, the measured VX component does change, goes down here and comes back. This is the jet in the X component. Since the current sheet can be oriented any which way, you actually see that jet also in the VY, and you see the current also in the BY. So that's why we want to rotate things from the measured system to an optimum system, so that all those changes that are in one component. In this case, cluster was here on the day side. Okay, so in order to say, well, is this a reconnection jet or not? We compare the measured velocity with the Alvean speed. And if it's the Alvean speed, because that's what the outflow should be, with sweet Parker-wise, then you can say, yeah, there's a reconnection exhaust. So here's what I did. If you just look at the two bottom panels now, this is a prediction in red and from one side and a prediction in blue from the other side. And that's this comparison with the Alvean speed relative to the outside. And it matches the black dots, the measurements, really well. So this is a reconnection event, and I'm putting all of the data together. But you see there are differences. If you only had one spacecraft, you wouldn't know that. Flying a formation is important for various different things. If they're close nearby, you can see that there's structure now at this scale. If we time shift the data relative to one spacecraft, we get the time differences, and we know there's separation in space. That's important. I'll get to that in a minute. It's timing analysis. But here I've shifted all the data to spacecraft black, red by 36 seconds, backward, blue positive by 17 seconds. Now they all match up to one time right here. Okay. So when you're interested in timing analysis, you want to find a gradient in any parameter, like a sharp gradient that you can see at all spacecraft. You follow that sharp change and you shift it to that. This is a good paper, set of papers in 1998. It's a PDF file. You should really get to it. Find it. It has a lot of good methods. If you're interested in looking at data with formation, go find this. This is from chapter 10, Stephen Schwartz, where you can now actually use these differences. You can use the differences of your separation between the two spacecraft 1 and 2 to find the normal of that boundary. Now that's why this is important, because you want to know that normal. You want to see how thick it is, for example, in a normal width. You need that normal. Okay, and you also know the time differences. So setting up that matrix, here's the matrix of the separations, and the time differences. You can solve that by inverting this separation matrix, and you get now a normal, and that's what it looks like. It's plus or minus, and it's moving at a total speed of 59 kilometers per second. How does that compare to the normal that I used? 11 degrees off. Which one is right? Hard to tell. That's being an observationalist, right? You need to nail that. Well, why is that better than that? Okay, that's the work that we observationalist people, we do that all the time. Why should I trust that and not that? The caveats here of using the timing method is that, well, you need a really sharp gradient that's observed at all the 4 spacecraft that you have in your formation. Also, if the formation is not in a tetrahedron, if they're all aligned on a string, right, then it's a poorly defined problem, because the current sheet could be at some other angle. So well, if you're lucky, it moves across all of them at once, 0 time difference all at once. Or if it's pointing in this direction, well, you can't get that normal. So you need a separated spacecraft to do this. MMS, the last few minutes here. And this is what we're going to work on a little bit here this afternoon. This is an event that I just found recently that I'm looking at. So here's finding MMS data. This is the orbit in the XY plane. It's situated right here in the XY system. Now, this is the mean pause boundary. For assumed pressure, dynamic pressure, and activity, but it moves, it fluctuates all the time. So at this time, MMS crossed the mean pause. So here's the mean pause. You go from the ions, this is the mean sheath, and then you go into the mean sphere. This is a high energy plasma sheet. You see that the density and log scale changes dramatically over here, and the temperature goes up. So you go from the mean sheath into the mean sphere. You cross the mean pause. Here's the rotation of the field. It's negative on the mean sheath side, and it's positive on the other side. And here's your jet. Again, it's seen in all 3 components. And I want to rotate things so that they're in the L. The jet is in the L direction. Also, what MMS measures is the electron velocity and the electric field. So the electron velocity also see that jet. It's about 500 kilometers per second here. The ion jet is also roughly on that same order. So the ions and electrons tend to follow each other here. But let's look at this in detail. Here's the tetrahedron formation at this time. TQF, what's that? tetrahedron quality factor. It's only 0.76. A regular tetrahedron would have 1.000. So it's not perfect. Later in the mission, they were actively controlling them so that they're a little bit higher in this region of interest. Now, let's look at the current from a kilometer. And I'm just doing this in L so that you see the jet in the L direction here. This is the BL the component, the rotation. Now, this panel is important. This is a curl from the kilometer technique at the cadence of the ions, DIS, that's the ion instrument. You see a negative green signature here, and it's JM negative because my M is pointing positive this way, but the current is going the other way. So now we're actually measuring the magnetosphere current density right here. It's about 0.4 microamps per square meter. In this panel here, the second panel from the bottom, I'm comparing all four spacecrafts' local measurement of the current density with that curl. And here I use the burst. So the thick black line is from the kilometer. And you can see that in this region, some spacecraft has a current pointing this way, the other pointing the other way. What is the curl doing? In the middle. Question? Yes. M is along the magnetopause, and L is the maximum direction change. So you get that from maximum variance analysis, for example. So it's that direction in space that has the biggest change in a component of the field. That's L. N is normal to that, and maybe it's the direction of the least variance. Maybe, often used, but maybe I'm cautious. M is then the third direction of that. So it's a orthogonal system. We call M the outer plane direction. And typically, that's a direction where you want to see the Hall field perturbations. It's along the magnetopause, in this case, pointing that. So back to this black solid line. You can see that in this region where there's a lot of activity, a lot of things happening, that black line is the average of the actual current density. Oh, yeah, you got to be careful when you use a kilometer, and in this case, we see that the divergence of B, we can get divergence having the formation. Now, that divergence spikes up here. It should be flat and zero. You know that from Ampere's law. There are no magnetic charges. So here's the divergence B is big. And that's a signaling that there's you can't trust the kilometer there. Well, in a way, you can trust it because it's still the average. Here is the L component of that, and again, it follows it beautifully in most of the time, but not in that region where there's a lot of activity, and where divergence B is not equal to zero. Here's the last component of that. So from this tetrahedron, we can get an average current density from the kilometer technique, not instantaneous. The JFPI from the particle instruments does give you instantaneous current density information. And one can confirm if divergence is zero or not. Yeah, so this event, did we see all these signatures? So for example, here we cross through this region, we have a southward jet. It's going negative here, so it's a southward jet. So yeah, we see the southward jet. We see, what do we see in the electric field in a normal sense? Well, in the simulation, should be slightly blue, negative, and then we go into the Hall electric field, a positive, strong, positive here. So do we see that? Well, here's our EN panel. So yes, we see that negative blue region, and then it changes over to a positive. So it actually continues here. So there's a positive Hall electric field here. We see the convective electric field here. We also actually see the measured electron streaming toward the X line on this outward side in a positive L direction. Now what you want to do is you want to compare for the frozen in sake. That's what the three next panels do. In the three components, you compare the measured electric field with VI cross B in green and the VE cross B in red. You sum those two, or they should be on top of each other, then it's a frozen in situation. If the electric field is not on top of that, it's not frozen in anymore. That's important to do if you want to know if the fields are frozen in or not. So for example, here we have the ions are following here along, so they're frozen in, but here they are not. They're deviating. So why are they doing that? Well, in the asymmetric sense, the X-line has shifted. It's not symmetric anymore, so that the diffusion region in the X-line is actually shifted towards the magnetosphere side. That's what that could be. So if you add the VE cross B term to the measured electric field, you get the stuff here. And if it's not zero, again, it's not frozen in. That means that the electrons sense an electric field. They can get accelerated, they can get heated. And I think I should stop here soon. Just lastly, J dot E prime. So what's J dot E? Well, J dot E is the J from the current density, from the electric field. It's a measure of diffusion, dissipation. So if that's a positive term, you have energy going from the electromagnetic fields into the particles. If that term is negative, and yes, it can be, that changes directions, actually, right? So now you have a generator. So your particles lose energy to the magnetic field. And so that's what happens here at 3, but let's go MMS 4. Now you start seeing here, see the J dot E prime here on the bottom. We see that lighting up in 1, 2, and maybe 3 regions. In the X line, we expect that to happen. It looks like we have 3 X lines. The J dot E prime is not a single measure of whether or not you're on the X line. It means that the fields are not frozen in, but that can happen not just at the X line, it can happen on other places too. It happens in this case at the separatrix surface. So MMS2 sees a very strong signature here in the middle. It's in the beginning of the exhaust, so it's at the edge of it, close to the center of the current sheet. And what else you can do, this is my last slide, what else you can do with the formation flying mission is you can get the curl, the rotation of the measured electron velocity at all the vertices of your formation. So now you get a vorticity, meaning that there could be a small scale electron vortex motions. And so that's what this seems to suggest, that you have electron vorticity going on here in several regions. So MMS allows unprecedented examinations of the kinetic physics associated with the reconnection and space physics in general. It's not just reconnection, you can use it for many other things too. This example has demonstrated so many predicted peak signatures of reconnection. It demonstrated because of electron flow, vorticity, and an extended layer, because we know where the satellites are, that we know that that layer where that J dot E prime was not just at MMS2, it was also at MMS1. Separation between the two, it's about 10 DE. In summary, what we've done here today is I've talked about current sheets. I started talking about the heliosphere current sheet. It was thick, several hundred DI thick. It cannot reconnect. That's what they thought in 2001, but it does. Parker has shown that it reconnects close to the sun, very often actually. You see these enormous exhaust regions across a really thick layer. How is that possible? Question mark. No one knows. That's why we're scientists. There's still things to look for. The galvanic jets I showed along the current sheet are a major characteristic. Other reconnection parameters include the Hall magnetic field, and if you have a good measurement of the electric field, you can get the Hall electric field. But many missions don't fly 3D booms. You have a spacecraft spinning. That's what most people do. They have big, long booms in the spin plane of the satellites. But how do you get the probe to measure the potential in two spaces and dividing that over that distance? You get the electric field, but you can't do that easily along the spin axis. There's no centripetal force pulling your probe up. So many missions do not have a full 3D measurement. MMS has a really fancy device to move those probes up far away from the spacecraft. You want to be far away from the spacecraft. Why? Yep. There are a lot, when you put something in space, it's going to affect the environment. So you're trying to measure the environment with that disturbance from the spacecraft itself sitting in space. Yeah, you want to be far away from it, as far as you can. What else did I show? I talked about multi-spacecraft tetrahedron. Any good quality factor is important, but not all are regular. Divergence could not, sometimes is not zero as a result. So the generalized Ohm's law, I went over that a little bit quickly. Gives you the terms of that, of the generalized Ohm's law, what those electric field terms are when it's not V cross B. And I showed two examples of reconnection jets in the solar wind and the mini-pulse. And lots of stuff. But I'll be here all day, and so we can talk about this more.
Time for some questions.
Yeah, I have a question with the PIC simulation that you showed, the magnetic reconnection. I'm curious, does it start with that sort of unstable X spot and then let it evolve, or does it actually get to the X? Like, does it start like equilibrium and then you kind of force it?
Yes.
Then?
You first start with as close as possible to maybe, for example, for a force-free situation, so that it's in pressure balance. But you can do two things. You can disturb it, or you can make it really narrow. If you have a really narrow layer to start with, it spontaneously reconnects in many places. It's tearing mode. You can also, if you have a slightly thicker layer, you can sort of drive it. And yeah, many people also they put a disturbance, the vector potential. So you focus it to one.
Yeah, so we were talking about collimator technique where we have 4 satellites. What if we have 3 satellites or 2 satellites? What technique can we use to find the current? And also, you know, like what is the minimum distance or what is the maximum distance that should be apart to find the current?
Very good question, both of them. The second question first, maximum or minimum distance. Yeah, and it depends on what you are after. You're trying to look for something small. And if they're too far apart, there could have been a lot of evolution of the signature in between. Okay, so it depends. It's not a simple answer to that. If you're looking at big structures, a CME surface going by, you know, if they're too close, then you're measuring the same thing of that big structure. So those are the two extremes of that. It's from case to case, right? So in this case, with the MMS data, I can only say that, yeah, that layer where there was a big J dot A prime was probably at least that long, maybe longer. But I cannot put in a paper that it was this when I only measured that. The first question, oh yeah, 3, 4, how many do you need? So to get really the rotation of the magnetic field, curl of B, you need 4. Okay? If one stopped working, you can't get it from that technique. I'd be very, very careful. I wouldn't go there.
Okay, so I study currents at Mars using one spacecraft to the best of my ability. So my question for you is, do you see these reconnection events in particular locations? Like, because we try to do this from a statistical point of view, right? Because we have one spacecraft. So is it happening at specific local times with specific conditions, some latitude, right, that you see that you go after?
I would say everywhere, or maybe nowhere. I mean, it's space is full of current sheets, but the conditions sort of need to be right. If you have okay, some people have studied the Kelvin-Helmholtz instability. Okay, what is that? Shear. Velocity is streaming by. Okay, that's really hard for reconnection to get going in that environment. Here, there are special circumstances. I measured some. I use single spacecraft in the solar wind. I've used the WIND satellite. And you can see current sheets. You don't need 4 to see them. You have a current sheet. You look at the signal. Yes, you know that at that particular location where the spacecraft crossed that current sheet, there was a jet going away from an X-line region. When it comes to Mars, Saturn's magnetopause. People have been trying to look for reconnection jets at the Saturn's magnetopause too. I don't know what. Well, again, you need the good instrumentation, get good moments to be able to that you trust, and with air analysis and that stuff. But I think the Saturn's magnetopause is also in Jupiter too, is that you have a very different environment in its magnetosphere compared to the Earth. Maybe that's playing a role.
So we're going to take a 8-minute break. We do have, after the second lecture, about 45 minutes for more Q&A. And so write down your questions for Stefan. But let's come back. Let's come back at 1/4 after.
Yeah, please come see me with any questions. I'll be here. Here. Hi.
So actually,
Yeah.
I did the exercise with 3 spacecraft at L1 to see the work. So unfortunately, like 3-1 for the point. And 3, the spacecraft are aligned like this, and you had a crossing.
Okay.
You might get more signal.
Yeah.
So you do actually get signal.
Mm-hmm.
And I did this when like we had large CMEs passing. So
See, my question to you is then, what is your divergence of B? You know, so, right?
yeah, because so we had a internal discussion.
Yeah.
And so they calculate stuff.
But how, or if the moments are good at 3 spacecraft? Oh, but you don't have the electrons. Like,
Oh, not particle measurements to the end.
right. I mean, what you always can do is the local delta B over X, Y, Z.
Yeah.
Rough estimate.
Yeah,
Less
but
than-
the thing is, we had some people who were very skeptical
Mm.
to use kilometer
Oh,
scales
no,
than
no.
kinetic
Right.
scales. So
That's right. I didn't mention that, but if the farther apart they are, there's just too much things that can happen in that volume. So one current here is not the same.
I was actually going to ask your opinion of that. I'm kind of in like
Mhm.
invested too much time in that. Some
Right.
people are proposing this. Accuracy is needed to get currents, but I think they believe it. Waves propagate, and then you like
Mhm.
completely disentangle
Mhm.
the other positions.
Right. Yeah, it worked in this, so if you compare that, so I was like, well, not lucky, I used it because it's good. But MMS then has the moments, right? Right. So then I could compare with that. And so it's nice to see what you actually get the average. But not when there's a lot of activity. Oh, well, it's still the average, but you don't know what it is.
Dinesh,
Oh, yeah.
so I mainly work with KHIs, and
Oh, yeah.
so my next project is actually going to be like looking at definitely magnetic reconnection is one of them.
Yeah.
Yeah, and so we are doing a statistical study of different events. So
But if you have you know, good formation, so if you have a good tetrahedron factor, I think that Stephen they put that you know is his source of that number. Then you can get kilometer, and you can see that in you see a spike in the current that's indicating, okay, here's a current sheet. If there's a current sheet, then you go and look at the ion data. And if the ion data doesn't show anything, well, it could be that the electrons see.
So like one quick question. When it comes to KH and all sorts of problems. Like they don't have like some people go with the element and some people choose. And with KHIs, because my magnetospheres itself kind of gets twisted and rolled into the whole report. How do you go about choosing like which is appropriate coordinate system for
I did that for the paper I wrote. I really you know I remember that question of hey, join the discussion. So I was moving it because into you know so that you get the shear maximum kind of shear direction and get that as one direction. But I think it's in the appendix.
you mean the 8th sector?
Yeah.
I
Yeah.
would definitely. My advisor, he really hates that.
Yeah, I know he does. I've been at meetings with him, not bad. Uh-huh. Yeah. So for the menopause, for example, you know, so I just showed you that you know simple schematic, you know, from the side. So here's the Earth's magnetic field, you know, and that's the Earth's magnetic field. So here's the X, and here's the Z. Looking at the magnetosphere from the side, and of course when you have tail. So the Earth's magnetic field is pointing northward. This is a side view. So so in the classic example, we think that there's an IMF southward. Okay? So that means that these two can be put together. And so the biggest shear, it's at here. But when so the field is very seldom just like that. The field could be any direction. So then instead of looking at it from the side like this, you know, people look from the front. So let's look at the menopause from the front instead. That would be Z, and this X is pointing at you, X, Y. Did I get that right? No. So in what people do then is that, well, you know, the Earth's magnetic field is pointing this way, and it's pointing, you know, toward the pole, toward the funnel, toward the cusp, and it's pointing in the other direction here. Pointing, that's pointing away. It's pointing away. Okay. So it's pointing away here and pointing toward there, like that. So if you don't have a magnetic field that looks like that, is that actually that's northward. Forget that. Here's a southward component with a negative y. This was my y. So then by is then negative. So what you now look, you put this across here, and you say, okay, where are my regions of maximum shear? Okay, so that would then be in let's see, it would be this region, right? Here and here. So it would be here and here. So the field is pointing everywhere like that. So the maximum shear region would be here and in this sector here. Because here the magnetic field is pointing, the Earth's magnetic field is pointing this direction, but this is pointing the other. Yeah. So this is now the maximum. So this is where you would expect to have a reconnection X line. Northward, northward. We think of it mostly northward, but it can happen for southward too. There are cases. It's just a little bit more complicated because when you have a southward field, you can still drive a shear, okay? But then when you have a southward field, you can get reconnection going. So that reconnection then stirs things up and it kind of destroys that shear from really fully developing these nice big vortices.
Go grab something. We're going to start in a minute.
Yeah.
If I can grab.
Yeah. Yeah, yeah. Okay. Nope.
Lectures and
Okay.
checking on some
Okay, everyone, we're going to get started with the second lecture of Wednesday. One of the things for the activity yesterday, hopefully, even if you have not dived into RBSP, energetic particle data, or solar wind data before, hopefully you have the confidence now of knowing where to go and that there are tools designed in IDL, Python, as well as GUIs that allow you to read files with no knowledge of what the CDF format is. So you should feel confident diving into the data. But as you saw today, we have all these line plots or color spectrograms, and we make a story that we have a diffusion region of this dimension with a current sheet with these jets coming out on this magnetopause, right? So all of the things that are in the textbook, the drawings, the schematics, those were somebody's imagination that looked at a lot of data, right? And so we have a boundary layer instead of an actual sheet or a shock, right? There's some thickness. Well, how do you know? So somebody looked at it, and is it true all the time? No, right? There's always going to be cases that are going to be clean or not. And a lot of the times with single spacecraft, when you're flying through a boundary, you don't know that orientation. You don't know its motion relative to the spacecraft. So you could have very different signatures for the same thing. So that's why we're going and sort of need multiple spacecraft. But before I dive in, talking about scale sizes, just briefly talk about inclusive excellence. One of the things that we all aspire to is excellence. And one of the problems of our institutions right now is our very narrow definition of excellence. And so how do we redefine and start thinking about what does it make or what do we need to make a community that actually can excel? And so let's see if this works. Let's see. So quickly, how are you evaluated? So if you're thinking about grad school, a fellowship, a postdoc, your next job, how are you evaluated? With that? Publications, was that what you guys? Okay, so how do you include that on your cover letter? Is it part of your CV that you have works well with others? Right? So one of the problems is that our excellence is focused on quantitative things, right? And so the name of the game has always been publications. And if I want to evaluate the quality of your work, you need a body of work. And is that one paper? Is that sufficient to be able to evaluate if you have the technical skills or the quantitative skills or the data visualization skills, or do you need 2 papers or 3 papers, right? So we've always played this game of more is better. And there's 2 laws of economics. And the second law of economics is more is better. If $1 is good, $2 is better. If $2 is better, $5 is even better, right? And so one of the problems is we have this never-ending arms race where we don't actually have a bar. What does it take to get an NPP at Goddard? 4 papers? 8 papers, 10 papers, right? And so now I have a lot of pressure. Oh my God, I just talked to the person next to me and they already have 4 papers. There's no way I'm gonna, right? So we start having a lot of anxiety, a lot of stress, and all different types of issues. But Shirley Malcolm is with the American Association, well, what is it? It's the American Association for the Advancement of Science, AAAS. And instead of valuing what we measure, we need to measure what we value. So how do we redefine excellence to have this inclusive excellence, to actually have a community that's going to be able to solve the problems that we want to solve as heliophysicists? We need people who can do the good science, but we also need people who can bring together and be a good team leader. Be able to communicate our science, not only to people in our community, but Congress people and the public, right? All these different aspects and qualities. So how do we do that? And so that's one of our challenges. And it's not what we think of in terms of meritocracy right now. It's that the best will rise to the top. How do we figure that out? How do we change it? So what do you think the purpose of highlighting the careers yesterday? So Stuart and Allison sort of giving their career path. What message did you hear? You're gonna fail. Yeah, because often we have role models and they're, oh, I want to be like that person. And they obviously were the president of their kindergarten class, right? I mean, they won every award forever. But I'm starting at 22 or however old you are. How am I ever going to compete? And Allison also mentioned imposter syndrome, that obviously you're the intelligentsia of the human race, right? How many physics PhDs are there in the world? And you're going to be solving a lot of the problems for the future. So you've already rose to the top. And so it's, oh my God, how am I going to compete? They were valedictorian and they were valedictorian, you know, what's going on, right? So this imposter syndrome is something that happens to everyone, right? You always have to think about, I'm new, what do I have to contribute? I'm a student, my CV is only 1 page, how, you know, whatever, right? But recognizing that everybody started that way, how to go. So I'm not necessarily a good role model. You can talk to different people in the field, and they often have very different career paths that are not very linear. I'm very linear. And I'm different than you in a lot of different ways. And I was at your stage at a very different time in solar and space physics. I was thinking my first AGU meeting, the SPA sessions were on Cathedral Hill Hotel, right? We were in a hotel in San Francisco, right? We weren't in the Moscone Center, there wasn't one. And so the field was just so much smaller, under 5,000 people at fall AGU or something like that. So things have changed. But if we can start thinking about this definition of excellence to include other aspects of what you can contribute. And so we would like to reward the folks who are willing to spend a day talking with students and early career colleagues, right? Willing to answer an email because you get as you're developing it. But how do we put that on your CV? How do we actually put that on the rubric for awards or hiring? So that's the challenge. So the message I'm here is just, I'm different, you're all different. But this was my straight path. I knew I wanted to be a scientist since 3rd grade. So Mr. Navarro was my 3rd grade teacher. And I just knew it from there. Went off to college. Both my parents have graduate degrees, not yet, not PhDs. They're a Lutheran minister and a physician's assistant. And so it was pretty depressing growing up because my dad had a big church and there were weddings and baptisms, but there were a lot of funerals. And my mom was a geriatric oncologist, right? So she was mostly a social worker. So it was like, who died this week was the conversation. But obviously school was important. And I published my first paper in 1987. I was just looking at it and it's interesting. It was one of the early HSOs. It was actually using data from, I think, 1979. And it wasn't an MHD code. It was a hydrodynamic code of essentially with a magnetic field. And we didn't talk about coronal mass ejections or anything. We just talked about flares were blasted off from the sun and it had a perturbation in the solar wind and try to figure out what was that propagation direction so it would hit Helios 1 and 2 impate and Voyager 2. And at the time, Voyager 2 hadn't even made it to Mars yet. So kind of strange. But that was the first paper. And then I was an undergraduate research assistant for most of my undergrad, worked with Shinaka Sofu making AE, Aurora Electrojet. And that was when there was pre-PC. So the magnetometer was a pen on a drum and it had an ink well, and it rotated once per day. And you would go to your magnetogram and put a new piece of paper on every day. So you had stacks of magnetograms, but then they developed the computer and you started digitizing them. And that's what I did, is I digitized it. And I learned right then, never trust any data. Because there was some undergraduate working for 6 hours in a dark room digitizing it. And what was worse, the Russian magnetograms, there was some Russian undergraduate who would take the magnetogram from Vostok, put a piece of rice paper on it and trace over that, and then mail that to us. So I was tracing a trace, right? Oh, okay. So how many storms have we published? But I also looked at all-sky camera data and Aurora, so I knew I wanted to be a space physicist. I went to BU and sort of switched gears, studied IC3 and impate data in the magnetotail. And there are 9 Moldwin and Hughes papers, which are essentially came out of my dissertation. And so I had a lot of options for a postdoc, right? You have 9 papers coming out, come talk to me. I want to hire you, right? We still have this really weird bias. It's like, oh yeah, you must be a good scientist. You're able to crank out some science. But I did a postdoc at Los Alamos and sort of switched gears. started looking at geosynchronous energetic particle data and plasma data with Michelle Thompson. But Ulysses was also just launched, and it was going out to Jupiter during its ecliptic phase to be thrown out of the ecliptic plane. And so we had all this cruise data. And so started looking at the solar wind data, and we discovered there's these non-coronal mass ejection flux ropes that are really teeny in the solar wind, these small scale flux ropes, and started looking at Jovian bow shock interactions, and 19 papers came out of that postdoc, right? And so suddenly you're kind of competitive for that next step. Then I became an assistant professor, but there were over 360 applicants for that position in the early 90s. And I was actually the second candidate. The first choice candidate turned it down, Ray Lopez. And so it was a weird time in the early 90s. The Berlin Wall fell and people were not retiring. A whole bunch of Soviet emigres were coming to the US. And then I took advantage of a faculty member. You're not paid over this summer, so you have to be entrepreneurial. And I spent several summers at Los Alamos as a faculty fellow, spent a summer at Goddard as a visiting scientist, spent a summer at KSC studying lightning, and moved on. And I've had, I think, about 85 funded major projects over the 30-something years. And what's been great is I've have literally hundreds of students and postdocs and collaborators. You look at your network of paper co-authors, right? And that's what science is about, right? Is we can't do it by ourselves. Start sharing your emails and your cell phone numbers with these people that say, boy, oh boy, they were really good on that speed ass thing. I'm gonna figure out how to collaborate and solve with them. But I've also had well over 100 unsuccessful proposals. I think this summer I've received a bunch, and some of them are more painful than others. If you have an Explorer class and you get selected for a phase A study, that means it's a small number, and then there's a down select. You didn't get selected. It's just like, how many years of your life, and then when's the next time you can do it? So those are painful. And my first 6 proposals as an assistant professor were rejected. And so at that time, I finally did what everybody said I should do. I picked up the phone and called Mary Malott, who is the program manager at NASA for SR&T. And she said, oh, it would be great if you served on a review panel, but we only select people who have been funded in the program. And I said, ooh, that's kind of a catch-22. And so NASA developed this executive secretary position where they could bring early career people in to sit in on it. So I got to sit in on a review panel and started getting proposals funded. A volunteer, let the program managers know they are always looking for people who have the expertise and the time. And just knowing what makes a good proposal, what's the difference between an excellent and a very good, right? What's a competitive proposal? So try to do that. So how do you survive explosions and failures? Very zen. Just let everything fall like water off a duck's back. Learn from it, and then ask for help. So the 2 big things I learned early on is write a little bit every day. So that just should be part of your workflow. And even if it's 10, 15 minutes, you should be writing. So if you're a student right now, you should have your dissertation written. Or at least you should have chapter 1, chapter 2, chapter 3, a LaTeX or whatever it is, because you know what you're doing. Have the method, I'm going to be using this model, and this paper is relevant, and you can just start writing it. It probably won't ever make it into the paper, but it helps you structure, and you just start going. But be persistent, as everybody has said. Don't judge yourself against anybody else in this room. Everyone is different, and your opportunities, a lot of it is based on timing, and you have no control over the timing, right? So do as well as you can and for help. Okay, so what I wanted to do today is have you guys think as heliophysicists, space physicists, and talk about how we determine scale sizes. And I already mentioned this conceptual framework, this way of organizing ideas in a hierarchy. So go from big to small or small to big, or a way to think of components of a subsystem is often a really good way of organizing new ideas. So what I'd like you to do is introduce yourselves. You're at new tables if you haven't talked to yourself, and tell them the time and length scale of your research. And so what processes, what structures do you study? And you usually can tell the type of physicist you're talking to by the units of distance and time they keep in their head. Right, so if you think in angstroms and nanometers, you're probably a spectroscopist. I think in mega parsecs, you're a cosmologist, right? I mean, you just start thinking about that. So what units are just, you have a good feeling? Is it C over omega P? I mean, what is it, right? So I'll give you about 4 minutes.
Handing out MPPs like a lot. They have all the money for COVID when they weren't able to hand them out. Apparently, it's the best time to apply. Yes.
Yeah. Okay, everyone, if we could get a volunteer, what structure or process do you study and what's the unit? And let's do it just for 2 of them. Just give your time and space scale and we'll try to guess what you study. Who wants to play Price is Right?
Do we want to use the catch box? for
Oh,
this?
yes, we should have a boom box. So watch out, you have water. What units of time and space? Yeah. seconds to minutes in solar radii, so that's kind of a giveaway. But what do you think he studies?
Yeah.
Want to just hand it off to?
Me?
Yep.
Well, time scale from seconds to days, and in spatial scale from centimeters to kilometers. Ha 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 ha.
Okay, anybody want to guess? Substorms? Atmospheric chemistry?
Plasma bubbles in this region, in the ionosphere.
Okay, okay, so equatorial instabilities, okay. So the other thing you saw, some of the equations. One of the first questions I ask if I'm on a dissertation committee is what is your time scales and length scales? Because all of your equations of motion, your momentum equation, have a lot of terms. And usually you can neglect many of them because they're not relevant for your scale, right? And if you include a collision term, then I know what type of physics you're doing opposed if I can neglect all those things, right? So are you thinking big or are you thinking little, right? So think about your generalized Ohm's law and your momentum equation and what you can neglect. And yesterday, Stuart mentioned a bunch of dimensionless numbers. And almost all of those dimensionless numbers are ratios of the different terms in those equations. And when it's big, one term dominates over the other. When it's small, right? So that's all those are. So is it a high Reynolds number? Is it a high Alfvénic Mach number? Right? We have these dimensionless numbers that tell you what's important. Okay, so the structure and processes. So you can think and go through the entire heliophysics textbook. And we have active regions and magnetospheres and current sheets and all types of things that we've talked about that are physical places, regions, structures. And then we've been talking about, well, what's the physics that changes that? And we've just heard about reconnection, right? And reconnection seems to be a universal process. It's a way to rapidly convert magnetic energy into particle kinetic energy, right? So we can get these fast flows. But it also changes the connection, the topology of the system. So you can get a lot of dynamics. So just like a good criminal prosecutor that follows the money, physicists follow the energy. So how did I get that flare? How did I get that substorm? How did I get that ultra relativistic electron? Right? I have to start thinking about, well, where is the free energy that I can convert? You know, is it waves or what is it? And so that's a lot of the papers that you can write are these mystery novels. I wonder why there's a crap bite out in the particle distribution when whatever happened, right? And so then I can start thinking about reasonable processes that would do that and say, oh my God, none of them work. And so then I can start, am I wrong? Is the instrument data in error? You know, what's going on? Or is there some other physics that we haven't yet figured out? So your career is going to change quite a bit. Yep, Sky. Oh, that's fantastic. You're going to save somebody a lot of time. Yep. Nope. Yeah. If it doesn't work out, and even if you have an incomplete story, but you went down a few rabbit holes, that's worth, right? And then your conclusions could even help you in the future or a student saying, I looked at these two mechanisms and it's probably worthwhile looking at this third, but we don't yet have the computational capabilities of doing, or whatever it is, right? And then off you can go as a project for an undergrad that when you start supervising people. But you can start thinking about, I'm a Martian, you know, or you study things at Mars, or you're an outer planets person, or you know, a reconnection person, and I don't care if it's at the magnetopause or in the current sheet, I just want. Or you can start thinking about instrumentation. I build electric field instruments, I build time of flight mass spectrometers, whatever it is, right? And so I've started building magnetometers. So this is my Michigan license plate. I'm also a big X-Men fan. But the magnetic field is the most important variable in the universe. Everybody agree? Right? It's sort of the Obi-Wan Kenobi. It's this force that is everywhere, it permeates us. But it defines all the plasma boundaries, right? And then you need to know B for a lot of the key parameters, the plasma beta, alphane velocity, particle frequencies, et cetera. And we live on a magnetic planet in a magnetic solar system, in a magnetized galaxy, in a magnetized universe, right? So these magnetic fields are everywhere, and we've learned with reconnection, it's one of the most efficient ways to rapidly get a lot of energy out. So if you're an astrophysicist looking at some exotic process to make a cosmic ray or a gamma ray flash, there's not a lot of things that can, you know, I need to have things colliding or something, have shock waves going off, but how do I get a lot of energy? I can convert it. And if you look at the total energy density in the magnetic field, you only need less than 1% of the photospheric field or to get a flare. I mean, so you don't even need to be efficient at it. There's a lot of energy there. So what I'm going to do in terms of scales for the next 30 minutes is just talk about magnetic fields, but you could be thinking in terms of plasmas and particles as well. So one of the goals of physics, and there's a question to physicists, when will you know physics is over? What will be the end of physics? And a lot of physicists say, well, when we unify all of our understanding into a universal law, we're done, right? But we always try to simplify. That's what makes us physicists. We would be biologists if we like to classify, there's this species of spider has an extra hair on that third leg or whatever. But lightning is static electricity. It's the same, right? We like to generalize and try to make universal things. So wrote a paper in 2009 saying there are 3 fundamental structures in the universe, magnetic structures. There are cavities, so essentially a body that has an intrinsic magnetic field due to either a dynamo process or some other way to generate currents that holds off the plasma and the magnetic field of its surrounding environment. So a heliosphere, a magnetosphere, a astrosphere. And all you need is a little bit of shear between magnetic fields, and Ampere's law says I need a current. Or I have current sheets everywhere, right? Some are thick, some are thin, some are solar system scale, heliosphere scale, some are very localized, but there are current sheets everywhere. And then sort of the quanta of magnetic structures are flux tubes. So where you think about this frozen in flux condition, I have a bunch of plasma and it's moving along with this magnetic field and it knows I am on this magnetic field somehow. And I can get twisted all around, but unless reconnection happens, I'm on that flux tube, right? I'm defined. I can do my solar energetic particle tracing back to the source on the sun, even if I'm going across AU, right? So we have this fundamental unit of flux tubes. So these magnetospheres come in, as we said, all types of scale sizes, and it's like a Russian nesting doll, right? We literally have a galactic magnetic field. And all of the stars around us have their own astrospheres, right? They have stellar radiation going out and stellar winds, magnetized plasma interacting with the interstellar medium. We can see these heliopauses, these termination shocks, these bow waves. And inside, the planets either have intrinsic magnetic fields or induced magnetic fields or remnant magnetic fields, but everyone has some type of magnetic field that gets a chance to hold off either the Jovian magnetic field environment or whatnot. So just this scale size is going from small to large. And then even on the sun, we have pictures. And what are you looking at in images like this from your X-ray? So you see those brightenings, and they map out the magnetic field of the sun. Sky. You're looking at photons, and those photons are been energized through a variety of processes, but they're emitting light in loops. But these are sort of mapping out, painting the magnetic field. And we heard earlier that essentially everything on the sun is because magnetic fields get tangled up. And if you get a tangled up magnetic field, you have a flare. You have a big prominence go off. You make flux ropes and magnetic clouds and coronal mass ejections. So magnetic fields. So when you think about magnetic energy, this magnetic energy, B squared over 2 mu naught, same equation, same units as magnetic pressure. We want to know how things change. We have this dB/dt. So we talk about spatial scales. The other thing we talk about is time scales. But we want to know, is sweet Parker all we can get? Or can I get an explosive reconnection? Can I get a dB/dt where dt is really small? Get rid of a lot of B really quickly. How do I do it? Well, let's look at the physics. There's two ways of doing it. I can transport things out, right? My del cross electric field, or I can diffuse it away. So my Laplacian, so this del squared B. How do I get that eta? How do I get my resistivity to be really big? How do I diffuse this away? So we have anomalous resistivity as terms. So we have anomalous everywhere. Whenever something is not what we expect, we just throw anomalous on it, and then it says, oh yeah, we should have known. Or we'll still call it anomalous cosmic ray or whatever it is. Yeah. But we go back to your physics. So this is that Stewart bell. So what is the time scale of transport on the sun compared to diffusion? So has everybody used a screwdriver to pick up a screw to be able to get it into a part where you can't hold it? You magnetize the end of your screwdriver, and it's like, woohoo. And then you put it in your toolbox, and you come back a month later, and the screws doesn't stick anymore. So you have to remagnetize it, right? So that is the time scale of this magnetic diffusion. How long does it take for that metal to lose its magnetic field? And so Mars has a remnant magnetic field, and we can make approximations on what that diffusion timescales are. So when did it have a magnetic field? So we can try to use that to invert sort of geophysics of it. So we saw this picture here. This is what makes exciting things happen. And what a lot of you are going to be studying: solar energetic particle events, coronal mass ejections, geomagnetic storms, substorms. What energizes the particles that make the ring current, make the aurora, right? That's what space physicists, if I'm an astronaut going to Mars, where am I worried about that radiation? Galactic cosmic rays. Anybody know where galactic cosmic rays come from? Somewhere outside, but what is it? Who knows? We can't go. Damn. But we can do all types of things, right? But pretty much everything is converting magnetic energy. And there's an entire field that's trying to understand the generation of magnetic fields, the creation and destruction of magnetic fields. So you can sort of think of the time scales of billions of years in terms of our solar system. Why is there an 11-year solar cycle? What's that intrinsic 11 years? Why not 5 years? Why not every month does the polar field flip? Why not every decade the Earth's field flip, right? What determines those timescales? So that's what they're doing. They're trying to develop a dynamo theory to figure out these timescales. Is it the twisting of the field? Is it some alpha process of, is it the convection of the sun? What is the velocity of the underlying gas at the tachocline? How would I know? Develop helioseismology. I can look at these magnetic field perturbations, these Doppler shifts, infer what's going on in the sun, right? So those are all of the questions that are out there, and many of them are still the $64,000 question. We don't understand these intrinsic timescales. What gives rise to it? So, we have any maths PhDs here? Engineering PhDs? So where else do we come from? Geology, earth science? Everybody have physics-ish in your degree name? Do you guys think in equations? Trained that way? So when you're on an airplane coming into Denver, you look out at the airplane wind and start thinking Bernoulli? Wondering what that pressure difference is? Or most people don't. But as physicists, this is not your first go-to. This should be your second go-to. I want to know what's the intrinsic timescale of repeat of substorms. Why are there 4 to 6 a day? What determines that scale? Look at energy. Look at how do I get an instability? Is there an instability growth rate? Growth rate has a rate, a time, right? What will be driving that? Is it something linear or is it something non-linear? So I'm going to have to do some actual math. But we have all the physics that describe things, and we've been figuring out that for a lot of processes, we need to include very specific terms. And a lot of it is technological. You know, if we could do full kinetic tracking every electron and have Avogadro's numbers worth of particles flying around a global system, we would do it, right? It would be kind of cool. It's kind of a waste of time because we figured out cheap ways. But if computation was cheap, then we don't need to make approximations of mass ratios or anything. We could just do it. So this is where that creativity, that decision-making process. If I neglect this term, can I explain my thoughts? This is your validation. I have a model and I can have a whole bunch of currents, let's say, and I fly a satellite through it. And I can, a cool thing about a model is I can turn currents off. What if I turn the ring current off? Or what if I turn off the Pedersen currents or whatever it is? Do I still get the signature that I have? Yes or no? And then I know what it is, right? So which term is important? So you've seen these, your Maxwell's equations, you know how to solve them. Any of you have to solve this set of equations as part of a qualifying exam? Oh, that. So we have all of these different scale sizes and structures, but how do you measure the scale size of the magnetic field in the solar wind? So tell your neighbor from your textbook, classwork, or research, what is the overall structure of the IMF? And you got some clues already. And what are the time and space scales that are important for the interplanetary magnetic field? And then more importantly, how do we know? Made it into a textbook. So I'm going to give you 2 minutes.
Yeah, that's true. In space scales, I think the velocity is usually kilometers per second. Yeah.
Measurements.
All of it.
Yeah.
Like a few particles per centimeter cube.
Well, that's close to 30. Closer to the sun, it's like 10.
Oh, yeah. I mean, because it expands. Yeah.
Yeah. It doesn't have to start.
So it's very obvious that we do Earths.
Yeah, yeah.
So when I say, what is the global structure of the interplanetary magnetic field, what picture pops into your head? Parker spiral. So you can be looking down on it, you can, due to the rotation, and these radial field lines are going up, but the footprints. So now looking from the side, what do you picture comes into play? So the ballerina current sheet, right? So we have this offset between the magnetic axis and the rotation axis. So we start flopping up and down. How do we know that? How do we make these three-dimensional pictures? Okay, so who do you think of when you think of IMF in terms of equations that describe the structure, how the radial and the azimuthal component of the IMF falls off with distance and varies as latitude? Parker, right? So you can go back to Parker's original papers and look at his equations and look at his hydrodynamic solutions and whatnot and pull it out, and MHD would do it, right? You can start putting these things in. So all of these equations come in. But we have a model that we can run and try to visualize it, but we also have single point things. And I can see there's a toward IMF. So the IMF is going towards the sun, and then occasionally I cross a current sheet and it's going the other way. And sometimes I see it once per solar rotation. Sometimes I see it twice per solar, right? So I can have there must be some wavy structure to it, right? So then I can start thinking about source surface maps and making magnetograms, right? So the first, I think we're about 100 years since the first observations of the Zeeman effect of the sun. So we're getting close. So the first time we are able to do that, and we have a new mission coming up, EASY, that's going to be using the Zeeman effect to image the magnetic field in the auroral electrojet. And that's one of the goals. If you can make an image, right? It's because everything we have are line plots. Then you make a picture of the magnetosphere, of the magnetic field, right? And so the power of SDO and SOHO and Hinode and everything else is we have images. So can we do it? But from a single spacecraft, we do these things over and over again, statistically. So our large scale structure of the heliosphere, essentially we've been assuming it's a sphere or a teardrop, and Marav Ofer has published a croissant theory of what we actually look at like with the interconnection of the interplanetary magnetic field with the interstellar magnetic field and the flow relative motion of the sun around the center of our galaxy. We go around the center of our galaxy about once every 250 million years. So in the age of the Earth, we've gone around 18 times. So happy 18th galactic birthday, Earth. But what's kind of cool is that, as you know, that we have spiral arms, but we're not a rigid rotating with everything moving, right? So we have relative motion of the stars, and about every 7 million years, we have a close encounter with another star system that can perturb our Oort cloud and all types of things. So we have a lot of dynamics going on over this long history that we have no idea how dynamic this shape is. Do we go through dense regions of the interstellar medium? Is there regions where there's more neutrals that then get ionized as they come in? So bigger pickup ions, so we have bigger, right? So there are all these dynamics that we're just taking a snapshot in the last 50 years of the space age. So this rotating and waving current sheet gives rise to this large scale structure. And thinking about this large scale structure in terms of space weather or understanding what's going to happen at Earth. We know we like IMF BZ south. How do I get IMF BZ south? Just let me wrap. And if I had a completely planar structure, I'll get some tilt. I could have bubbles put into this. I could have flux ropes. And so Joe Borofsky tried to visualize what is the fine scale structure, thinking about this quanta. And he essentially took a whole bunch of rubber bands and twisted them all up and cut them to see how they went around. And you get this spaghetti diagram. Right? So these flux tubes, as long as they're not reconnecting, are just floating along independently. And you can color them. One came from this longitude, from this latitude, this came from this active region, this came from this coronal hole, or whatever it is. Right? I can paint those flux tubes. But suddenly, now when I'm thinking about the small scale structure, there's magnetic shear everywhere. Right? All the flux tubes are not all parallel to each other. They have just a little bit of shear. So Ampere's law says I need a current sheet at the boundary of all my flux tubes. The definition of these flux tubes is this current sheet. So I can have potentially small scale reconnection throughout. I have this large scale HCS that's really thick. And I have little bursts. Could I have nano flares or whatever, right? So looking at things at different scales, you start seeing that there can be energy conversion at different scales. And then of course we have these transients and their structures. And a number of you are studying and modeling these coronal mass ejections. Trying to think about how do they actually, or how are they generated? How do they propagate? How do they evolve between the sun and one AU? If they're a fast CME, they're going to be driving a shock. What is the interplay between that shock and that magnetosheath region of this thing? And what is the geomagnetic effect of that when it hits Earth? And these guys are huge, right? They fill the sky, right? We have halo CMEs that fill the sky as they're coming at us. And we're trying to model what the IMF is at L1 with your model, right? So we make huge assumptions that thing that can be a quarter of an AU, right? In terms of curvature radius is what's hitting the magnetopause. We have these CMEs, their sheaths. Are they still connected at both ends of the sun? We can start talking about magnetic flux and conservation of flux. We can think about these flux ropes. And so if I have a flux tube and I have a current, I'm going to get a twist, right? So you put your thumb in the direction of current, you get a magnetic field, I add it to, I get a helical structure. So we have flux ropes everywhere. And those flux ropes have these complicated geometries and ability to trap particles. Shocks and CIRs or SIRs, a lot of discontinuities and rotational effects. And then, as you heard, turbulence, right? So keep on going down your spectrum of scale sizes from the largest scale to the smallest scale. What is the smallest relevant scale size of a plasma? You could think of Debye length in terms of the electromagnetics. And start thinking about this diffusion scale in terms of gyro radii of electrons. You can start thinking of collision frequencies depending on the density, right? You have this mean free path, right? But you get down into the really teeny numbers. So the scale that heliophysicists deal with is unbelievable in temperature, density, time, and distance. Many, 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 many orders of magnitude. And so when you start thinking about this turbulence, where does it come from? What role does it play in the global structure of the systems? All types of things. So what can you determine with one spacecraft? So that was a question. You're flying through a magnetic structure, a flux rope, a current sheet, a boundary of a magnetosphere. What can you tell me with one spacecraft? Okay, so I will be in one region and then I'm in another. Something changed across a boundary. And so when you think of the original sort of a cluster flying around, pop through the magnetopause every orbit. And so I can start building up a statistics that, hey, the plasma pause is at this distance, at this local time, with this solar wind, right? So I can, it's a structure there. It's dynamic, but it's always there. One of the problems with a single spacecraft is I could see a change in the magnetic field. That's not due to a spatial gradient, due to a time change. So you have this time-space ambiguity, and we've been dealing with it all our career. And that's one of the biggest issues and drivers for clusters and MMS. And why 9 spacecraft, right? How many different scales do you need, and how many different tetrahedrons will you need? So almost all of, you can figure out thickness and all types of things with one, but boy, you need to make a lot of assumptions. I'm going to assume I'm perpendicular, that the object is stationary with respect to my relative motion, all types of things, which clearly is not true, but you can make them. With 2, it helps if they're on pearls on a string and, you know, like both see the same thing at the same time, or if they pop in one after the other, right? We can do this timing difference analysis. With 3, you now can do some 2-dimensional type of rotation. With 4, you can start doing curls. You get gradients in all 3 dimensions, right? But we do it. And so a lot of the original papers were IC1 and IC2 spacecraft, and we made assumptions. So a lot of the early pictures could be completely wrong. That's what we have in our textbooks. This is what you actually look at. This is a bunch of IMF data, BX, BY, BZ. Can anybody tell me what you're looking at? The time scale is hour tick marks or big tick marks. So just descriptively, what do you see? You have a total field of a few nanotesla. There's something going on at a few places that are relatively sharp changes, and BY has this very rapid sign change. Yeah. Okay, yeah, so you have a rotation in BZ, a little one, it's negative, and then it goes through 0, and then it's strong. Right, so this is the data, and people put pictures to it. This is a current sheet crossing or not. This is a discontinuity. This is a shock. And so we develop relationships. If it is a shock, the Rankine-Huguenot relationship should hold, and I can test it. What's on one side or the other? If it is a magnetic flux rope, I can model a magnetic flux rope and fly through it and try to fit it, or whatever it is, right? We can do it, but this is it. This is all you get. And you make all the pictures. Are these real? What are those nanotesla, very rapid, at the cadence of the instrument that's going up and down? Are those waves? Are they EMIC waves? Are they mirror mode waves? What are they? What would you do to identify them? Develop a model. This type of wave, I would expect that there's a shear or a electron beam or a T-perp over T-parallel or whatever it is, right? And you would grab the ancillary data and you'd say, yeah, that's it. And then you can start, I don't need the plasma wave data or the plasma data anymore. I know what they look like in the magnetic field, right? So you start saying things, but as a student, how in the hell do you know what it is? There's a long history of people looking at it. And so if you're going to be diving into data, you should look at a lot of data. What does the typical MMS orbit look like? So when it's going through the day side, what do I see? What does a substorm look like? What does a storm look like? What does an EMIC wave look like? How do I know it's the bow shock and not the magnetopause? What does the magnetosheath look like? And right, all of these things are going to have some signatures. And the problem is it's going to depend on local time. It's going to depend on solar wind conditions, right? All different things change. So you have to get a sense of where am I? What's going on? So I'm not sure how many time series of MMS you've looked at, but you look at a lot of it. And so we have a whole bunch of this Heliophysics System Observatory. And so now I not only have BX, BY, BZ from MMS 1, 2, 3, 4, but I also have Themis, ABC, Artemis, Discover. How do I put it all together, right? So that's your challenge. And so we develop tools, visualization tools, to look at the large scale structure of things coming from the sun. We can put planets and spacecraft. And so this is what I did for that first paper in 1987. Very early version of this. We had 4 spacecraft and try to look at how perturbations propagated out, how they interacted, because there was a fast stream going into the slow solar wind. We can start thinking about the off the ecliptic plane. So if you have 2 or more, do better than 1, but we still have to make assumptions. One of the basic assumptions is that every structure is an infinite plane. How valid is that? Depends on the scale, right? So the Earth is flat on our scale, right? So that's a pretty good assumption. The violation of the curvature over the room size is nothing, right? So that's a good assumption for a lot of problems. But is it valid for your problem? Depends. So just detangling length and time. Here's a time series of IMF-BZ looking at wind and ACE at L1. And this is actually a correlation coefficient between BZ, between the 2 spacecraft. So they're both at L1, and the correlation can go to crap and usually above 0.75 or whatever. There really that much structure in the solar wind that things that are tens of RE apart, maybe 100 RE apart, see different things? Yes. There's a lot of fine scale structure. So if you're going to be running a model from an L1 observation to drive MATS-RS, wind will give you one, and ACE will give you another. One has a BZ north and one has a BZ south. You're going to get very different results, right? So being very cognizant of this. So we live in a magnetized plasma universe, and essentially you guys are magnetized plasma physicists. And so the magnetic field is a key parameter and defines all of the structures and determines a bunch of the dynamics and scales. So almost every heliophysics mission has a magnetometer because you need that sense of where am I in the system. So as you go forward, your instrument's going to be the most important parameter. I need to know the electric field, damn it, because I want to be able to clearly find this Hall E field. And boy, wouldn't it be great if I had long booms. Some of you can figure out, can I develop a stacer boom that can extend tens of meters or some other way of getting a rigid boom? So think about scale size, dynamics, and magnetic fields. Great. So we're going to now go into questions for both talks. Okay. So it's not directed towards me.
No, it actually is.
Okay. Oh,
So I've actually been, so I haven't really read this, found any like nice definition yet. What is the definition of a flux rope?
a flux rope is just a twisted flux tube.
But then it's kind of the same thing then, because
They're essentially the same thing.
Yeah.
Or you could have different twists and you can essentially have a null, but it's, so any type of axial current in a flux tube is going to give you twist. And so what is that core field? What is that axial field? So you can think about field aligned current on Earth. Have a current running along the field. Going to add some twist. That's a transverse wave. That's an Alfvén wave. So this field line current carries energies driving particles. I need the motion of electrons to get that. But I can think of it as an Alfvén wave, right? It's, you know, the same stuff, depending on how you look. Touchdown.
I have a question for Stefan. So I'm not sure if we covered this or not, but I'm wondering what drives or what controls the speed of a plasma jet from reconnection, and is there a lot of variability in speeds for different reconnection events?
If you can grab the.
Good question. The outflow speed of the jet is going to be dictated more or less by the Alfvén speed of the upstream plasma. So it's the inflow region. So it's the B little, subscript of the I. So that's the Alfvén speed. But the whole system is then moving with the background flow. So it's relative to that. Not sure if that answers the question.
That's one of the tests that you can do is compare it to the Alfvén velocity to say, yes, it's the jet.
So do we observe these jets in the heliospheric current sets as well, like from 1 AU? Do you observe this?
Do we observe these jets across the heliospheric current sheet here?
Yeah, frequently.
Okay, it's a complicated story. When you're close to the sun, maybe I should use this. Yeah, thank you. So if you're close to the sun and you have Parker Solar Probe, and you look at the magnetic field for the current sheet, but you use something else too to understand the topology of the structure, and that's the so-called electron strahl. The electron strahl is suprathermal particles at temperatures of 70 eV or more, and they're constantly streaming away from the sun. Okay, so they're coloring your field direction and helping you understand the topology. So close to the sun, when you compare the strahl with a magnetic field across one of the heliospheric current sheets, they're sort of one-to-one, often, fairly often. When you're at 1 AU, that has been complicated for a long time. That the so-called sector boundary, when you look at the straw, if you just look at the electrons, yeah, they see that it's 180 before and 0 after. But the magnetic field does not follow that. It's much more complicated. Why? Okay, that's still unknown a little bit. But we do see big jets near at 1 AU too, in terms of reconnection jets.
Yeah, and so when the pitch angle distributions, as you're looking at the superthermal straw, it's going away from the sun. So if it's a closed field, you should see bidirectional streaming, right? It's connected at both feeds. And then if you see a unidirectional and you're crossing a current sheet, it's going to be going to the other direction, right? So you can use that sort of to map that magnetic field. And Taifan and Jack Gosling has looked at the wind data and the very high time resolution data and have published evidence of jets at very small scales in the solar wind. And so it's still highly debated is what type, is there reconnection across the current sheet? Are there places where you could have a fast solar wind stream compressing the current sheet? And at the small scale, can you get, even Kelvin Helmholtz, the shear can be suppressing it, but if I make a roll and the shear goes away, but now I have a detangled, twisted flux tube, you could, and I think you've published on that.
Okay, ready?
I have a specific question about the magnetic field at a CME onset. So normally the rotation of the magnetic field, I believe, is considered to be like the remnant structure of a flux rope, maybe of a prominence that was erupted. How would we be able to distinguish that from, let's say, the same effect of field line draping of like the CME? So if the CME is coming along and there's an ambient magnetic field and it kind of rotates in order to drape across the front of the CME, how do we know that, like, wouldn't that be captured by it as well? And how would we be able to differentiate between the two?
Yep. So the relative motion of the ejecta with respect to the background field, if you're plowing through it, you're going to get everything draped over it. We think about sort of snow plowing the plasma, but that plasma is tied to a magnetic field. So you can get this draping effect. So you can get a intensification not only of density and solar wind dynamic pressure, but you could actually get an enhancement of B, right? And if the field happens to be southward, those become very geo-effective. And when you think of the overall orientation of a flux rope, it's a rotating the first part, let's say it's a northward field in the front, and then it's going to be a southward field in the back. So every magnetic Hale cycle, the polarity of the sun's field switches. So during one solar cycle phase, you're going to have first northward, then southward, and the other one you're going to have first southward, then northward. Does it make a difference in terms of geo-effectiveness? So all types of things. So velocities, and then the overall orientation. Important. These guys are big compared to the Earth. So
Okay. For both of you standing up here, I wanted to ask, there's like the age-old question of how to describe our, heliosphere through magnetic fields or through currents. I'm the person that sees the world in currents. Do you think that what are the benefits of describing this in one way versus the other? And how should you visualize and how can we connect the two sort of cartoons we have in our head?
What are you thinking? BV or EJ?
Well, I think in terms of B, you know, that's the magnetic field is a powerful descriptor of the system, I think.
Yeah, and there is a Parker paper on different paradigms, the EJBV.
Exactly.
yeah. But usually, in one sense, it's a chicken and the egg. It's curl B equals mu, not J. So you could think in either. But one of the nice things with the magnetometer is they measure currents. So
Right.
Correctly, I don't have to get a distribution function of ions and electrons and look at differences in velocities.
Do you think that we leave anything out by, I feel like the community's really leaned towards B field, B cross B kind of motions instead. Is there something being left behind by only thinking that way?
It's gotten better, and maybe Allison and Christina can chime in too, that there was sort of the school of thought of sort of MHD, everything's MHD. And so I can neglect that really the particle distributions aren't Maxwellian and all that stuff. And what's crazy is it shouldn't work in the solar wind, but it does. And so what are the roles of these, one collision per AU, but really turns into a million collisions if you think about it. But there are some still in the community that would argue that the MHD is the wrong way of thinking about it, because you can't violate frozen in flux. I can't get reconnection with the true ideal MHD, right? So I have to introduce something crazy.
I would chime in on saying that it's really scales within scales. And so it all in a way depends on what physics are you after and what are your tools to understand looking at.
Awesome. Yeah, thanks.
I'm just wondering, are there any magnetometers to measure the very weak coronal magnetic field, like in the order of 1 to 10 Gauss? That's the range we are talking about.
So, so all of the remote sensing of the stellar magnetic field is through the Zeeman splitting. And so you need to have a line that is at whatever depth or part of that solar atmosphere that is optically thin so you can see it. And so I think in the maybe in some coronal hot line, there would be a way to do it, but are there any coronal? Yeah.
Because we don't have any measurement for the world. Unfortunately, that's where a lot of the actions happen. Connecting, moving, groups are expanding.
But
apart from the Zeeman effect, is there any other way to use a magnetometer?
You'd have to get there.
Because it's like, wow, we have a spacecraft that's actually on that.
Right. Yeah.
But I mean, it's still a long ways from what's going on. So getting a lot of information, and it's doing all kinds of stuff that we did not think it was gonna do. You see all
Yeah. So here's sort of follow up on that, Christina, is that what will happen at the end of the Parker mission? Could you take the probe and just plunge it and measure as you go along? How deep could you get?
two problems. One is, sorry, there's a couple problems with that. One is that you'd have to be on the same side of this, in theory, you'd have to be on the same side of the sun as Earth so that you could send your antenna, sort of like what they did for the Huygens probe, right? Or whatever, what was the one on Jupiter that? Galileo, right? And so, so you can transmit as long as you can until your, thing basically fries. But the other problem is, okay, now I've got three problems. Okay, so the second problem is there's a lot of radio noise and stuff that's really close to the sun. So it's really hard to send your signal out and actually get it. The bigger problem is that in our infinite wisdom, and I'm putting myself in that even though I really had nothing to do with it, but I don't want to really throw everybody under the bus without me, or drive the bus as I throw them under the bus. But Parker Solar Probe was designed so that you cannot have the instruments on at the same time you're downloading the data. So every time they download the data, they turn all the instruments off. So fundamentally, no, we can't. I mean, we can plunge it down, but we're never going to see the data as that happens. So
What is the heat shield? What is it, sort of the specs of that? I mean, has anyone
like
looked
how
at
close can you
how close
get?
could that shield get?
Yeah, I don't know. I mean, that's a really good question as to whether, and one can make the argument of, would you want to try and lower that perigee even farther? Of course, once you've gone low enough and you can't swing by Venus anymore, I don't know how you would do it. So, but everything was sort of, so for a little bit of interest is that there was a question of like, when you're designing Parker Solar Probe, somebody has to make a decision. This is what we were talking about before, is like when you're designing an instrument or a mission, you have to have an idea of what questions do you want to answer and where do you need to go and what do you need to measure to do that. And one of the fundamental questions of Parker Solar Probe was, how close do you need to get to the sun, right? So yeah, it'd be great to go into like 2 solar radii, but that's engineeringly prohibitive, really, really hard. So, okay, so maybe it's pretty easy to go into 30 solar radii, but does that answer the questions you want to answer? So there was this big debate, well, not a big debate, but a lot of discussion about how far in is in far enough to answer some fundamental questions that you're still technologically capable of doing. And of course, at the time, we weren't capable of doing it. We had to invent this, heat shield and all this stuff. But 10 solar radii was actually picked for a particular reason. Most of the theorists were convinced that you would be inside what we call the Alfvén surface, right? So there's this transition of the corona between which you can probably explain this better than I do in terms of like communication, like the plasma cannot talk to where it came from once you cross this position. You can't send information back. So the plasma basically kind of loses its, like, it's if something outside the Alfvén surface, if something happens to it, that information can't propagate back down to the surface. Is that sort of
Yeah, I
roughly?
think that's close. Yeah.
Close enough.
close.
Okay.
The direction
So-
of the Alfvén waves, can you come back or?
Right, so it's propagation in the Alfvén waves, which you can think of as information going back and forth. So inside there, you can kind of talk back and forth, but once you get outside, you can't tell anybody what's going on. So the idea, so this is a theoretical surface based on a bunch of like really smart people making, calculations. And the idea was to get inside that position because the physics in theory really changes. Stuff really is very different inside that. And the question is, where is that? And so, a lot of people think it's at different places. There was evidence that it was probably anywhere between, I don't know, 10 and 30 or something solar radii. And then the feeling was that, if you took a vote, pretty much all the theorists said, well, for sure, it's outside 10 solar radii. So the decision was go to 10 solar radii. And then we took to the engineers and said, okay, based on that, can you build us a heat shield that'll keep everything, nice and cold and not melt? And amazingly, they managed to do so. Now, whether or not that heat shield would survive at 5 solar radii, I have no idea. The engineers, they're like, okay, you gave me a spec. I'm going to meet that spec and I'll probably exceed it, but I'm not going to promise anything. So, I don't know if they would ever agree to try to get in closer.
Yeah, so for that image of the eclipse, you can imagine that there's some place where you transition from the corona to the solar wind. And so if I want to touch the corona, how close do I have to get in this Alfvénic layers, the supersonic, so information can't come back, where inside things can be bouncing around. And what's the end of life of Parker Solar Probe is that it will run out of fuel and won't be able to keep the heat shield between it and the sun. And then everything will ablate away.
Yeah, and
except
we
for-
make a joke that our high energy particle instrument is suddenly going to measure a lot of aluminum, and carbon, and all these things that aren't supposed to be in the solar wind. Of course, we won't actually measure it because
it won't
we
fly.
won't get that
But
actually.
there will be the heat
It'll
shield
flag.
left and Justin Casper's Faraday cup.
Floating along.
One quick follow-up to the original question, and to get the magnetometers in there. You can measure it, you can model it, but you can also view it optically. So, Solar Orbiter is another mission, and they're seeing all these amazing small campfires. So you can get other information, but maybe not the magnetometer.
We'll go here and then up front.
I guess I just have a quick follow-up question. Has Parker Solar Probe then, like, is the theory right that it is lower than 10, or is it lower than that?
Yeah. At least temporarily cross through the Alfvén surface. And I'm losing track of my years. So that might have been last year, I think.
Did they
I
say
think
it
was
tasted the sun or touched the sun?
touch the sun,
Yeah,
touch,
yeah,
we don't
yeah,
taste,
yeah.
that's weird.
Well,
Yeah.
you're a chemist.
Yeah. So yeah, it was the big press release was solar, Parker Solar Probe has touched the sun or touched the corona. And basically that was determined by looking at the magnetic field and the plasma data and making these calculations and, calculating what the Alfvén speed should be and saying, wow, we went in an area that's really low. The thing is, the interesting thing is, as you've seen from a lot of these, plots that have gone by, is there are time periods where you are in a subalfanic region. So that has happened, but it's in the interplanetary medium and close to the sun, that's always been a transient, right? It's some structure, some, plasma of a particular kind that goes by. the sun should have a whole region that's, you know, so the big thing was saying, okay, we saw a suboceanic region. Is that a transient? Is it a temporal thing going past it, or is a region that we've actually crossed into? And there were a lot of arguments as to me that it was actually, we actually skimmed in and came out again. And there's been some subsequent things. We haven't gone in so that the entire, so the orbit's very elliptical, right? So there's only a certain time period where you would expect to be in close. And we haven't yet had an orbit where for every time period below, I'm just going to make up a number, 15 solar radii, you're always in a suboceanic time period. That hasn't happened. So, but the feeling now is, you know, it's not a nice, you know, pretty picture sphere. It's, you know, this really weird, jaggedy, wavy thing. And so we just happen across part of it that seemed to be, you know, within that size. So it was kind of cool.
So how do you make low alphane velocity? High density and low B, so a diamagnetic cavity, some dense plasma that's pushing out the magnetic field. So is that a transient?
Okay, just a follow-up question on the in situ measurements for the magnetometer. So I believe I picked this up in a few dinner a few lunches that I sat in. There's like calling it the Huygens probe for the sun, I think, of having the idea of sending out a mothership essentially, and then having smaller probes and having them dive into the corona and burn up, but just survive long enough to send data back. And I think from the materials perspective, it wasn't even the biggest problem. But the biggest problem is actually getting enough delta V to send it down within like a few years, because you need all these flybys to get your spacecraft to go close to the sun. And the getting back to telemetry. So, and there was a workshop, I think, even recently about that at Goddard. So people are working on that. I just don't know, not sure like what the time frame is that they're thinking of to actually decades, yeah. So, but there are people that are planning to do that, and maybe someday you'll have that.
Yeah, so weird thing about orbital dynamics, it's hard to get to the sun. Easy to go out. Any questions?
Explain the difference between the magnetograms you hope to capture of the aurora with the new mission and the things you digitized. I think you said those were magnetograms when you were undergrad.
Yep. Yeah, so magnetograms have different meanings. We talk about solar magnetograms and then the original paper magnetograms. But so right now everything's digital, right? We have a computer. And I think I mentioned it to you. So the PC was invented in the World Wide Web after I got my PhD, right? So almost all of the data you were looking at, and I mentioned CDAW, that was CDAW 8, I think, was my first one I participated at, and people brought IC data and IMP8 data and Guam magnetogram data, so you could figure, you know, and you just sat around a workshop and you wrote a paper. And so you guys were doing that yesterday, right? And so I was not really joking. You guys should write a paper. You know, if you dive into something and say, I don't understand that. You talk to the person, I don't understand that either. That could be an interesting puzzle, right? So there's not enough people to look at all the data. And there are a lot of funnies that you don't know, so you don't really write it up, because I don't even know where to begin, but it might look like one of your problems. So magnetograms are great, and one of the beauty, it's just essentially a time series of magnetic fields for the ground-based. We want them all over the place, but most of the Earth is ocean, and so I'd love to put a magnetometer on buoys and have them float around. One of the problems, though, is if you look at the sort of the wave spectra of a buoy bouncing around, it's in the ULF. So you need to have a really good understanding of your orientation, and you can do it now. Ring laser gyros are able to get that position, but they're export controlled, so you can't just throw them onto the ocean. So we're trying to figure out non-military use technology to figure it out, but if you can figure out, how do I know where I'm bouncing around? That would be great. Bottom of the ocean, it's salt water, so you have magnetic signatures of currents and stuff like that, so it can't be too deep. But
null results are really important, right? Because a lot of people do a lot of study, you know, we investigate a lot of things that don't pan out. But I gotta say, there's two problems with it. It's one, a lot of people don't value those papers, so they don't get written. The second thing is they're actually really hard to write because, you know, they're easy to go through the introduction and say why I'm looking at all this stuff, and then the, you know, instrumentation and the methodology and all that stuff, and then present your results. And then you have to write their conclusion. And it's really unsatisfying and really hard to write a conclusion, you know, or a discussion section that says, yeah, we thought this would be the case and we tried that and that didn't work and that doesn't show this, and, you know, and those kind of things. And it feels like it's just kind of hanging there. And you're always worried that if you're going to submit it to a referee, the referee is going to go, this is a piece of crap. They didn't conclude anything, you know, because you always think of scientific papers as solving some problem or advancing the field by, you know, concluding something or saying this. But the other way of advancing the field is to say, we tried all these things and they didn't work. And so we can remove those, or we can say, you know, don't look here because we've already spent a lot of time doing it. But I would say that a lot of those papers never get written, which to the detriment of our field.
They also don't get reviewed favorably. So that's the other problem. And so when you all start reviewing papers, keep this in mind, that null results are good, that small incremental steps are good and are still worthy of publication. You don't need to write a groundbreaking paper that's going to upend all of we understand about solar physics or whatever to get published. But I feel like the bar these days has become, you know, students have a really hard time getting papers through because they have to come up with some brand new insight that's never been thought of before, instead of doing something, you know, that has been done before, but with better resolution data that gives us more information, you know. But those are, I've seen my students struggle with this, and I don't understand what's happening in the reviewer community right now.
And it's not just students. I would say, you know, there's established scientists that are struggling with the same thing too, right? You know, yeah. So it is very frustrating. But you should still try.
The analogy I use is that you're writing, you want it to be a Picasso or a Matisse or a Van Gogh, right? You're looking for the muses to come visit you and have this thing. You're actually a house painter. And there's a process. I clean the walls, I spackle the walls, I tape it, I go get the brushes, I get the paint, and I just put it on, right? A lot of the things, you have a problem. I wonder if there's a difference between solar cycle, CME orientation of IMFBZ, first north, then south. I wonder. And then you can go do it, right? First you would look, did Janet Lumen do it or whatever? I think she did. But that's the process, right? We have a process. And so you can constantly be doing things. And as you're reading, they almost always are not conclusive, right? It's not. So what is that open question? And that's always, even as a referee myself, is the null result is we looked and it's not this idea. So it's probably this or that. And so you say, well, that kind of begs the question. Why don't you look to see if it's this or that, right? You know, and so you have to be firm and say, you know, that's the next study, right, or whatever.
I'm going to chime in here real quick before Sky asks your question there. That may have sounded really discouraging to all of you that papers don't get accepted. Then there are journals and there are journals, right? So if you're aiming for a Nature paper, the bar is really high. If you're doing a statistical study, then there's journal geophysical research in space physics or planetary, right? So there are many different journals. So don't get discouraged. If one turns you down, well, they may have a very valid point, the reviewers. So take those to heart, okay? Don't just like, well, they're, they don't know what they're talking about. They have clues for you in their reviews, and then you take them and you absorb them and you think, oh, maybe they're right. And then you submit it to another journal where it's more fitting for that result, perhaps, right? That's one thing. And the null result, I was kept thinking that, well, here's another null result. You go look for Saturn's magnetopause and you ask yourself, is reconnection occurring there? And then you do a statistical study, and if your instruments have the right cadences and you should be able to see these jets, and you don't find them, that's a null result. It's just gonna add that.
And Stuart Bell's paper on the limits of detection. I looked and I didn't find it, so I know it's not bigger than this because that's my limit. Scott?
Yeah, so just last comment, it's more to the senior scientist, I think.
Why are you looking at me?
Hello. And people in the room, but if my thesis is based on, and I'm lucky for this reason, that I get to run around and ask questions and read those null results from other people at LASP that never publish them. And so now I have a thesis and I'm trying to get all of them to publish their null results or put it in my work or do it myself. And how do I collaborate with them? And in this age of open science, I think we have to, put it out there. And that's how we answer those, open questions.
Yep. And the new inclusive term for senior scientists are experienced scientists. Established, yeah. Okay, yeah. Yeah, and the first law of economics is the relative value of money. So $1 for Bill Gates is not the same as $1 for a poor person on the street, right? And it's the same for papers. The value for a student of a paper is huge. But for a senior person, it's 292nd one, right? And so I bet you if you ask them, I would like to, take your unpublished work and actually get it into publication. I bet they say, oh, fantastic. So, here and there.
There's a problem we generally observe when we write our papers. Sometimes we can send our work to a reviewer to review. We get our materials from certain journals where we review works of other people. And when we quote these people, we get returns from the people that the reviewers that these ideas from already published authorities are wrong. So how do we validate those results, the comments of the reviewers, whether they are right or not?
How do you validate the referee comments? Or
I was about to kind of touch on the same thing, just keeping the conversation going. I noticed this isn't as much of an issue in engineering papers. There are lots of engineering papers that just say, I ran this test and we didn't see what we wanted. And I think just trying to think it through, it's not much of a personal slight. I don't care if the non-conductive epoxy changed the gain of my MCP or something like that. This is just a fact that is useful for the world. And I think that just having a mindset switch between the scientist perspective is more validating theories. Is that theory valuable to begin with? And was your hypothesis a good one? That whole kind of, it brings it into a side of judgment into the actual review process. You hear people say, well, this kind of information has already been published, or it's not relevant or something. Well, is that fundamental? Is it integral to the science? If as long as they're not copying the work, that's just because it's another data point. Why would that necessarily be grounds for rejection? How is it not just a personal opinion if this science is relevant enough for the field or something like that? I think there is a lot of personal biases that go into the review process. And I guess I don't know if an engineering mindset is the correct term, but yeah, I mean, if you go out to validate something and it doesn't end up being valid, that's science. Like, that's just data. Like, publish it, put it out in the world. I don't know why we would reject that at all, kind of thing. So
Yeah, perseverance, also engaging with the editor. If, you know, usually there's a meme of referee 1 and referee 2, right? The best thing ever and the worst thing ever. And then the editor has to make a decision on which one to weigh. And they might say, you know, please respond to referee 2's substantial criticism, or they say we're going to reject because referee 2. Engage with them, right? With that conversation. Okay, so last question.
Actually ran into the situation where like I got a very bad review comment. And it turns out like the reviewer is also a human. In this case, I probably know that it was an experienced scientist.
Established, I guess.
Or established, okay. And every single argument was completely wrong. And in this case, it was nice because I could actually prove it. But turns out there was a error in my paper, but not that one that he pointed out. So yeah, so in that case, it took me ages to get the paper published, but it did get published in the end. And it took a long time to argue against that, and it was a bit of a waste of a time to a certain extent, but it also made the paper a bit better. So everything the reviewer says doesn't have to be correct. And even I started reviewing papers just like, I think a few weeks after I got my first PhD. So some of these reviewers are also very young. So you have to take them with a grain of salt to a certain extent. And they could also, depending on how large your field is, it could also be a reviewer that's from an adjacent field who doesn't know the super specifics. And people don't get paid for the reviews. So I tried to sit down a few days and read a paper, but there's only so much limited time I can put into it. So I might also make some mistakes myself when doing this.
Yeah, in the different communities, AppJ has 1 referee and most of Space Physics Journal has 2, and there's benefit to get that referee 1 and referee 2. It's almost always makes it a better paper. But if you only have 1 referee, the editor that's it. And so figuring out how that works. Okay, so for the rest of today, we have lunch, and then we're going to come back. We're going to have some talks, student talks. So for the students that we're going to present your 2-ish, 3 slides, be prepared after break, and then we're going to have a activity at 2, I think. So lunch should be served.